Good morning to all present here. As you all know that we have gathered here today for the FDP on thermal characterization and advanced measurement techniques. I am Gautam Narayan Shetty, an undergraduate mechanical student from National Institute of Technology, Srinagar, would like to extend a hearty welcome to every one of you. First of all, I would like to express my gratitude towards the organizers of this FDP, Professor Adnan Koyab and Dr. Sheikh Shaikh Salim for their efforts in bringing together this esteemed group of experts and participants from different parts of the country. I would also like to thank AICTE, Training and Learning Academy, and ATAL Academy for sponsoring this event and making it possible. Till now, we have completed expert lectures delivered by Professor Hamid, Professor Rakesh Shegal, Professor Anju Shegal, Dr. Farooq Ahmad Nazar, Dr. Noor Zaman Khan, Professor Andalip Tariq, Dr. Ois Gulzar, and Professor Ahmad Wani, and a visit to HPCL bottling plant, Pampur. All these expert lectures were productive and fruitful. Today, we are on the fourth day of these offline sessions. I would like to welcome Dr. Junaid Hassan Masoodi to this FDP. After completing his bachelor's degree in mechanical engineering from the University of Kashmir, Srinagar in 2007, he joined TIPL and worked as site engineer for the erection and installation of 1,000 TPD cement plants. In August 2008, he joined MTech program in Mechanical System Design at National Institute of Technology, Srinagar, and in June 2010, he joined NHPC Limited as an engineer and was given assignment of operation of maintenance of 450 megawatt at Bulkhead hydroelectric power station. In December 2012, he joined the PhD program at National Institute of Technology, Srinagar. During his PhD studies, he established turbine erosion test laboratory at NIT Srinagar, for which the equipment worth rupees 1.5 crore has been installed. On 19th of April 2017, he joined as assistant professor in the Department of Mechanical Engineering, Institute of Technology, University of Kashmir, Srinagar. He had served as a technical expert trainer for mechanical CAD from February to May 2018 in India Skill, Jammu and Kashmir 2018, an initiative started by Skill Development Mission, Government of India. In May 2019, he completed his doctorate in mechanical engineering. He is also contributing as a reviewer of few reputed journals of Felsmere, ASME, etc. His area of interest includes erosive wear, design and development of test rig for qualification of wear in hydroturbines due to sediment and cavitations, compressible fluid flow, computational mechanics, computational fluid dynamics, analysis of turbomachinery, fracture and fatigue, crack plasticity, crack closure, single overload fatigue, crack growth retardation, and load interaction effects. Now I would request Dr. Junaid Hassan Masoodi to take up the dais and deliver his expert talk on 3D scanning for measurement of cavitation and abrasive wear in turbines.
Respected teachers, particularly Professor Adnan sir and Professor Mohsin, Dr. Mohsin, and my dear students and students and scholars. There are some scholars also. Very good morning and Assalamu alaikum. Okay, so actually, the topic for my this today's FTP program conducted by this Department of Mechanical Engineering at Srinagar is related to the 3D scanning of the as a measurement tool for assessment of cavitation and erosion damage of the turbomachinery performance. Okay. So since it's not particularly, I'm not going that deep into the this erosion damage and all that, how the calibration were and all the mechanism related to that. So I'm just trying some brief description how we can use the 3D scanner as a measurement tool for either it can be the cavitation or erosion damage, or it can be some other major parameters related to the turbomachinery, or also it can be applicable for other components which are related to other fields also, not particularly for these turbomachinery and all that. So first of all, I'm going to give a brief description how that is related to the 3D data acquisition techniques, the various 3D data acquisition techniques that we use as a measurement tools. Okay, so the classification related to like 3D data acquisition techniques includes the contact or tactile devices. So it can be the contact or tactile device, or it can be the non-contact or non-tactile devices. So in contact and non-tactile devices, we can have the coordinate measurement machines. For example, those machines where we can use the robotic arms or any other via the certain mechanical probes in order to get the 3D dimensions of any objects. For which we want to get certain dimensions, or for which we want to get certain 3D images. Okay. So those are because they have a direct contact with the objects for which we want to get the reasonable information, for we want to get the information that later we can develop in certain CAD models or anything else. So for that case we call those as contact or tactile devices. Okay. So then we can have another type where because there are certain limitations for that. Already we have to the particular mechanical probe or robotic arm have to be continuously in contact with a particular object, and there are certain limitations also that it can't actually go deep into the certain dimensions which are actually out of the scope of that particular these probes, mechanical probes rather. So in order to have those dimensions also, we can have the contact, non-contact or non-tactile devices, in which we can have the passive and active types. So in passive, we can have the we can have those measuring tools where we don't need any illumination from illumination sources. For example, light source or laser. So we can use the environmental light for getting the picture of that particular objects. So for that, for example, there is a for those passive measurement devices, we can have the photogrammetry. So as the name suggests, we can say it is a photogrammetry means to measure this. Grammetry means to and the metering means to measure. Grammetry means to actually we can say to get the graphs from that. So that the name suggests, we can get where we can use the photogrammetry in order to get the certain 3D images from by capturing certain images of the particular objects. Okay. So in those we can have the various examples of that. For example, we have got civil engineering surveying equipment that those use those what we call as the theodolites or dumpy levels. They can use the same techniques they use, where they will get some surveying maps for various lands or mountains, whatever. So we can, in those photogrammetry, we can have the stereo visions. So we can have the stereo visions, where we can say it is just like our eyes, but whatever we are seeing this time. For example, I am seeing just with my two eyes. Okay, so it is just stereo vision principle contains two cameras which view the same scene, detect a common 3D point on different 2D location. Okay, for example, we have got this is left camera and right camera. We want to see certain object for which we want to get certain information, for which we want to get certain distance, for which we want to get certain depth from a particular location. So for that, we actually this is a we can get actually it is based on the triangulations. Triangulation based on the triangulation between the two sensors, where we have got, for example, this is the one camera on left side, the right camera on the right side, where actually this is the line of projection. We want to get the picture of this at point P. So in order to get the distance between the baseline and this point P, so it actually intersects at point P. So this is the common, we can say, common line that intersects at that point. In order to get a certain distance, we can say it is equal to Z. The depth, we can say the depth is equal to this is the focal plane. T is the baseline, D is the disparity. Okay, disparity is actually the distance between the corresponding common plane, this distance between the that is xi and the xr, xi minus xr, which actually we can say that a common point, where distance between the common point, what the camera A sees and what the camera B sees. So distance between difference between those distance, we can say, is the disparity. Actually, we can say that it is this Z is equal to the inversely to the disparity. That means if we have got the disparity is very high, that means we can get the distance very low distance. If the distance is if the disparity is very small, we can get a very high resolution for a particular applications. Okay. So here we can say that we can say it is something like the we can say pixels of any camera, where which we can get the good resolution by actually decreasing the size of a one pixel. Accordingly, we can get a good resolution of that. So in this we can say the A and B camera is showing that what camera A sees and what camera B sees, and the common we have got the C. So if we want to increase the number of cameras, if we want to increase the number of cameras from all sides, so it is possible that we can get a clear image or we can get a 3D image for a particular object by applying this type of measurement tool, that's the stereo vision. Okay. Then there is the same example that they have shown the building, how there is a common point that whatever we see from our left eye and whatever we see from the left, that which is possible for us that we can at least get a distance between from my and at least we can assume that there is some distance. What is the distance between my from this end to that end? Which is not possible if we see the same thing via one camera. And it is possible if we apply the same thing by using the two or more cameras, we will be able to get certain more informations for a particular object. Okay. Next, we can say this is the triangulations. What are schematic triangulation process for the photogrammetry by two or more cameras, and there are the single point triangulations. We can apply the multi-point triangulation in order to get the various points, because we don't want to get only stick to the one point. We have to get the information of all the point, of all the vertices of any object. So for that case, we can have the multi-point triangulation. We can have the bundle adjustment of the triangulation. Okay. So then we can have the active part of this measurement tool of non-contactile devices. So in that case, we'll discuss some brief discussion regarding the laser scanning. We can discuss the interferometry, time of flight, phase shift, scanners, triangulation, all that, because we have to replace triangulation principle also. Is also applicable to that part also, because we have to replace now with camera with some light source. Okay, so there is, and again we can use the triangulation principle for that case also. So actually here the active devices are where we are using some some illumination source, some light source in order to get the certain information related regarding particular object. So for that case, if we see that what is this interferometry, where actually it uses the principle of interference, where we can get the different shapes of fringe and all that. These are some of the phase shifting interferometry, where or vertical scanning, and there are many other types where by which we can use this active mode of this measurement tool. Similarly, we can get the this is the time of flight. Again, we are using some light source, and we are using some receivers, or it can be the camera, where we are giving some reflected light to a particular object from which we want to get some information, and that particular light reflects back, and we can receive it from via this camera, and we can get the distance and many other information depending upon the various what are the normals and all that for a particular object. Then we can see the phase shift scanners. So again, the phase shift scanners are just like the time of jump. Here we are actually seeing how much amount of phase shift has taken place for a particular incident light. Okay, so by that case we can get certain information, whatever we want to see for a particular object. Then the another type is the triangulations. Triangulation, again we can use the triangulation, only we have to replace with another camera with a certain light source. The rest of the things remain same for calculating, for calculating certain distance and all that. So then there are other types, the photometric stereos. Okay, photometric stereos actually are the multiple image under different lighting source to resolve the ambiguity in the surface orientation, because for a particular object it's not possible we will get only the plane for that. So there are certain objects where there are different planes. So in order to get the particular shape of that object, it actually what does this photometric stereo does? It actually we actually use the various light source, and it's actually the image intensity, which is a function of various light source, surface normals, that means the normals via what is the inclination of those normals to that and the surface reflectance. So here it is shown that how this photometric stereo can do. It is an object, and these are the surface normals that we can get from this type of measuring tool. So here we can see the typical photometric stereo system containing two parts: the photometric stereo information capture system and the photometric stereo normal estimate algorithm. We can get the algorithm because it's not we are using only one camera, or we are getting we can get the different image by orienting this particular image in different directions, so that we can get a number of images. So we have to adjust those images, and we can get certain algorithm for that, and we can get a particular image out of that. So that can be a 3D or whatever we want to make out of that. So then is we can have another type, that is the shape from shadows. Okay, we know this how we can make the shadows when we were in our childhood. So we can use the same principle by having certain shadow perspective lines. We can use those, and we can get those. This is showing here the setup for shape for self shadowing using each of the several lights in turntable, and we can rotate this turntable, and we can get the various images or the various shadows on that particular translucent panel, and we can later on merge those various images, and we can get a certain 3 3D image of a particular object. Then we will discuss something related to the 3D scanning. Okay. So 3D scanner is a non-contact, non-destructive device that uses a laser, or it can use a source to accurately capture the shape of the physical object in the computer-aided CAD data. So it generates a point cloud or a set of data points in coordinate system that accurately depicts the physical object size and shape. Can collect the information about an item, about an object, highness, breadth, and depth, and captures the various coordinates of the points to calculate the dimensions and reconstruct its shape in 3D environment and define its position and space with all astronomical accuracy. So the 3D scanning actually does this by data capturing stage. It is having the data capturing stage, which samples the 3D world. It will have a data registration stage which aligns the various 3D views. Data merge stage which samples the aligned views into parametric models. So we will have some example of that. For example, here is the 3D scanning of this this cattle, we can say. So we can get, first of all, if you want to get the 3D scanning by using certain light sources, so we can get first of all some this polygon file .pli file. So it actually it incorporates various coordinates that we can get. We can get that, convert them into the data cloud. So point cloud, we can see it's showing here the various point clouds are there. Then we can join those point clouds and we can form those triangulations and all. So we can have some triangulations that we have generated from the point cloud. Then we can we can say that it is a kind of a mesh that we have formed. Okay. Then we have to actually go for the simplification of mesh, because in order to generate the 3D surface profile of those generated mesh, we should have it can lead to the more computational time, we can say. So for that, in order to simplify that, we have to simplify this mesh. So mesh simplification can be done in various parts. Okay. So one of the parts is, for example, vertex clustering is there. So where partial vertices, there is a mesh retelling and there is a mesh decimation. So I will discuss this. What is this mesh decimation? So in mesh decimation, we can say decimation quality refers to how accurately decimated mesh follows the input mesh, and processing time in polygon mesh. To lower the amount of triangles, actually we have to lower the amount of triangles that we have formed from the data cloud. So for that case, there are various removal techniques. We have got the vertex removal, where we can say we have to choose one. For example, we have chosen this vertex here. Then we have to actually remove this vertex. Then we have created some poles here. Then we have to again create another, so that we have to reduce the number of triangles there. So there is another, that is the edge collapse. So we have to actually merge the two vertices together. You can see this is one vertex, another vertex. So we can merge these vertices and it form a one vertex, and actually we have decreased the number of triangles. Then we can have the half edge collapse, where we can say that we are actually reducing on one side of this only one vertices we are actually reducing by combining with another vertices. Again, we are saying we are actually reducing the number of triangles. So this is the vertex removal. It can be shown here how it can be removed. So that means we have selected one vertex. Then it kind of a hole is created. Then we have shifted it to the इधर नहीं हो रहा, इधर आ रहा है, मुझे यहाँ पर डाउनलोड करो तो this is a kind of a hole that has been created. Now we have actually formed different triangles. Okay, now this is the another filling the hole with a new triangle. Then similarly we can have the half edge collapse. How we can move this vertices. I don't think it is. So then we can see it's showing here how we can move a particular edge in order to decrease the number of triangles. Then this is the same thing we can go there, but this is the vertex removal and reverse. We can go for the vertex insertion. Similarly, is the edge collapse, and we have got the vertex split, and this is the half edge collapse there. This is the restricted vertex split. So there are some 3D scanning, mesh decimation errors also. We can have the vertex error, which is the error because we have to actually decrease the particular number of triangles or number of mesh up to a certain limit. So if it crosses that limit, that means it will show us that there is an error has been formed. So that particular limit can be between the two vertices or number of more than two vertices, or it can be between the surfaces because there are surfaces also which connects various vertices, and there are the point between the points and the surfaces, and there are the vertex between the vertex plates. So these are some of the 3D scanning, this we can say mesh decimation errors. So I want to discuss here now whatever the facility we have got here. So this is the 3D scanning Comet L3D blue light scanner. that we have got. So actually we have used this scanner in order to get certain the damage of a particular this Pelton buckets and the sphere. Okay, so it was done by the Mohammed Zahabdin and under the guidance of this Professor G. A. Herman. So before that we were actually going for the traditional method of calculating the volume of the wear that has occurred for a particular turbine or for a particular turbo machine. But this technique actually improved the this we can say the improved the calculation which was based on the earlier, which was based on some traditional methods. Actually, by using this 3D scanner, it is possible now we can modify those already models available in the literature. We can modify because the amount of volume we are getting, the erosion volume which has occurred in a particular turbine, we are getting to some accurate level. That means we can modify those already available literature, various models. There are various models, and we can incorporate those models in the CFD analysis so that it will give us a very accurately we can measure those and the various we can say the erosion mechanism. We can have the good erosion mechanism, which erosion mechanisms have occurred for a particular turbine, because there can be the cavitation erosion also, there can be the erosion that can take place with the sediments. So, and there can be the synergistic effect between the cavitation and the sediment erosion. So for that it becomes very important for us to calculate the amount of wear that has occurred, and for that we need also other parameters also which are important. Parameters related to the turbo machine. Not only that we have to use this 3D scanner, we can get the particular data. We use other parameters that are the real data parameters for a particular runner. Okay, so this is the actually we have got this again we have got this. This is a kind of active mode of this we can say this data acquisition instruments. We can have the camera, blue light projector is there. Okay, then we can have the turbo. There is a tripod also. Okay, for this 3D scanner we can get certain illustration of the fringe projections, because whenever we use those blue light fringe patterns, so there is a deformation of those patterns. So ultimately that particular camera can see those deformation and calculate. We can calculate those in order to get the various image around the particular object. So for that we can use the turntable to turn the table in order to get the image to all around the surface of that particular object, or we can move this camera also, because it's not possible for various heavy objects to install this on turntables. For that we have to actually, and that is more important, that we have to calibrate that particular 3D scanner for each take. So these are some of the images that can be captured from 3D scanner. Okay, and whatever we have done. So this is the field study that has done for the eroded coating. This is showing the eroded coating of a particle, eroded splitter tip, severely eroded sphere is there, eroded nozzle is there. So this is the erosion, or we can say that can be the synergetic effect between the cavitation and the sediment erosion, showing for the earlier this was for the Chinani hydroelectric power station. This is for the UPS, that's a Woody power station, and this is the damage, the amount of damage that has taken place in the Dunosi power station, that is in Kishtawar. And these are the eroded Pelton runners, is showing that there is a wavy light and the scales that have been formed due to the erosion damage. Same thing we can see for the sphere and the nozzles of a Pelton bucket, Pelton wheel. So we can we actually go for the scanning of a Pelton turbine. So we install this Pelton wheel there, and we actually took certain image. This is the pictorial view of the 3D scanning process. Process involves scanning of Pelton buckets. It's showing here, and it is then we can see the development of a mesh as we have seen earlier how it actually generates first the data cloud, then go for the triangulations, then there is a development of mesh. So this is scanning, it's showing the scanning of a Pelton injector. So it's again we have the marker positions, and we can have the scanning of a sphere of a nozzle. Then we can have ultimately we have developed this 3D model of a particular scale, which is also showing here that how much amount of erosion damage has also been recorded using the 3D scanner. This is the process by which we can go through in order to get using the 3D scanner as our major tool for obtaining the various useful parameters related to the erosion damage or the cavitation damage. Then we actually compared, mapped this 3D model obtained from the 3D scanner, and that we mapped with the original dimensions of the sphere or the nozzles. Okay, so when we map those erosion, the original runner or the original sphere nozzle or the original turbine, when we map it with this picture, that is 3D image that we got from the 3D scanner. So same thing we did for this Pelton bucket. So then when we mapped, we got certain, then we subtracted the original volume and the eroded volume, and after subtraction we got actually this 4850.13 cubic centimeter was the original volume, and after erosion damage it was up to 4639 for the sphere. And for the nozzle, similarly, you can see 953.1 and 95905.06. That means the 48 it was for 180 cc for this sphere and 48 for nozzle. So this is the amount of erosion damage that has taken place by the sediment erosion of. So we actually got this sphere. This is also showing the sphere is eroded by 3.71%. Volume, and the nozzle is eroded by 5% of the original volume. It's showing here that when we subtracted the original, this is the eroded that we got from that. Okay, so it's showing loss of material. This is the blue mark is showing the original volume. When it was we can say newly sphere, and this is the eroded one. So in front of it. So you can see that there is a tip removal and there is a loss of material around its periphery also. And same thing happens here. We can see on on that side, we can get showing the blue color mark, so how much amount of erosion depth is there. That is minus 8.5. And from blue to green, you can see that we can get the various we can get the various important parameters related to the damage from using the 3D scanner. Same thing we can apply for the nozzle also. So we have taken here different sections in order to get the various other information. So it is showing here that the blue color mark showing that how much amount of erosion damage has occurred, and the green one is showing that in terms of the depth. It's showing here in terms of the all of this actually we have done in this using the 3D scanner. So here also it is the Pelton buckets. So I don't have to discuss here the erosion mechanism. Whatever the erosion has done, this erosion is more on the inlet side or outlet side. That is the secondary case. That depends upon the various other parameters. That is it. So here we want to discuss that how we can use this 3D scanning as a measurement tool for getting the erosion data. So here is also showing that the erosion is maximum erosion has taken place here at the outlet section because of the great relative velocity. Okay, so at the outlet, that is the more pronounced, you can have the erosion damage on this area. So this is the another data for it is particularly for the nozzle. It is actually we have opened the circumference and we have seen that the various how the erosion has taken, what are the crest and trough, that we can see the surface roughness, we can say rather. So we can get these data, we can also get from this. So these are the coordinates at various coordinates. What is the erosion depth for nozzle, for sphere, and for the Pelton bucket. And we have also used this 3D scanner for getting the, as we know that the for turbo machinery getting the various blade angles is it's not we can say for example, for if any particular product has been designed by a particular company, he has actually designed and he will not share any data to the particular for which he has to supply those data equipment. So in order to get those angles and all that and design the same machine component actually which match with the original one. So that was not possible there because this was a unimog clearing snow machine that was actually for the mechanical engineering department of Jammu and Kashmir department. They have damaged this radiator fan, and it is actually for Mercedes, I think. So they came to us and we actually used this 3D scanning machine, and we actually got the exact this 3D model of this particular machine, and we got this very similar parameters which can be the blade angles, whatever it is that is related to the turbo machine. So we got actually later on we can use those CAD model in order to replicate the same fan so that they can use this for their machine rather than obtaining the particular component that is also very costly. If they have to purchase only the fan of that. Okay, then we again use this 3D scan. This 3D scanning actually was done for the turbocharger because the turbocharger was very small. It was not possible for us to measure those dimensions, measure those angles. So we use this was only done by not 3D scanner. It was the pictures were taken by a simple camera, the iPhone or any whatever you have. So when the pictures were taken, we can say over 200 images were taken for that particular turbine. Later on the mushroom software was used, so in order to get the particular 3D image. So actually later it looks like this. So we got the 3D model of this turbo chargers, which looks actually something like this. So here I want to discuss here the we can't only, it's not I'm saying that we can use it for erosion damage or any other purpose. We can use 3D techniques, 3D scanner or other various this tools that I have discussed for various application also. Okay, so not limitation. It's not limited only to our field. So you can those students who are also doing research in other fields also, they can also use these techniques in order to solve their problems. Okay, so if we use this, we can later on we can use those whether it is for a static analysis or a dynamic analysis, whether it is for a CFD analysis, whatever it is, we can use these advanced measurement tools rather. So in order to solve our problem, in order to use as a research tool, so that the results that we will get later will be very accurate or will be very we can say helpful for us. Okay, that's the what I was actually going to discuss today. Thank you very much. Any other question?
lecture. Now,
if anyone has any questions, they can ask sir right now. Anyone? Okay, anyways, I have a question. So, out of all the techniques that you discussed, to find the depth, the stereo vision, and the other techniques that you discussed, which one is the cheapest?
Cheapest.
Yeah. Because I've already known about LiDAR sensors. They cost around.
Actually, if we look at the which one is cheapest, that is the at the end whatever we use, because we did in this mushroom software. It is a it's open source software.
Get the coordinates of a particular point. I'm not very much interested in the whole mesh. Okay, just for example, I have keys with me. I want to get the XYZ coordinates of these keys. Okay, so what will be the cheapest way to get?
You want to get the 3D model of that,
No,
or you want
just coordinates in the 3D space. Coordinates of XYZ coordinates.
coordinates?
Because for example, we already have X and Y coordinates. If we use one camera, okay, but we do not have Z coordinate. That is 2D. Okay, in order to get the Z coordinate, we use two cameras. Okay, and using disparity, concept of disparity, we get Z. Okay, so I actually tried to create this same model using Python, and I used two cameras, droid cams. Okay, but it was showing some sort of errors. Then I looked up to certain software that are already available, cameras that are already available. So we have that Intel Sense 435 for that disparity and all. Okay, but it was not working actually. Like, I just want to get the exact coordinates of these keys or any object in the space. What would be the cheapest method of to do it?
Cheapest method I can't say because I don't know exactly various equipments or that are and their costs which are available at this time. Actually, I was discussing only the various tools and their principles which were. So the cheapest which I thought among these was this which we used with a simple camera. So it's not only we are using the 3D data for that. So if you look into the deeper into that, it will give us the various coordinates of that also. So for example, this is a 3D scanned object that we got from the particular this camera, taking the number of photographs or using the particular mushroom software that is open source. But if we look into the deeper on the polygon this file of this, so it is actually the number of coordinates there. It's a text file. So we can get those whatever the data, the point you want to get from, you can get from that text file also. Later on, we actually the particular software use those text files to convert those in the point clouds and then into the mesh. It's actually the text file. It's actually the coordinates. Yeah.
File containing zeros and ones.
Exactly. It's a point.
RGB file
Actually, it's those X, Y, Z coordinates are there.
Why don't we use the cheapest?
Actually, the difference between those why we have gone for so costly things. What at the last we want to use the product we want to get should be very accurate and so that's what we can use, but this is only for a particular student which can't afford so much high costly. For that case, you can use those not to get those coordinates using those camera and all those open source software.
now I would request Dr. Motion Kansa to felicitate our expert speaker, Dr. Zunaid Masoodi. The next session will start in a few minutes, so I request everyone to take some small break. I would like to welcome Dr. Tanvir Rasool to this faculty development program. He has obtained his BTech in chemical engineering from Regional Engineering College, Srinagar in the year 2000 and MTech in chemical engineering from IIT Uttarakhand. And in 2014, he got his PhD for his thesis Evolution of Pyrolytic Behavior of Biomass Waste through Kinetic and Thermodynamic Analysis. In 2018, from National Institute of Technology, Srinagar, having started his career at REC Srinagar as an ad hoc lecturer in the year 2001, he became a permanent lecturer in 2002 at REC NIT Srinagar. He is presently in offering the laboratory courses as well. Presently, PhD scholars are registered under his guidance and has guided 3 MTech members to the Institution of Engineers, Indian Society for Technical Education, New Delhi, life member of Indian Institute of Chemical Engineers, Kolkata. His paper on mechanic study and absorption of zinc and nickel on algae sodium bentoate composite in ICEA CSC 2018 held at NIT Trichy in December 2018 was awarded the Best Paper Presentation Certificate. He has been serving in the Executive Council IE of Srinagar State Central for the past 14 years and was elected as Honorary Secretary for the Center of the session 2014 to 16. He is also the convener of DUGC in Chemical Engineering NIT Srinagar. He has chaired technical sessions in various national and international conferences. Now I would request Dr. Tanvir Rasool to take up the dais and deliver his expert talk on energy assessment of pyrolysis of biomass.
Thank you. Thank you.
Thank you for the introduction. Before I start my presentation, he has given my introduction, so I'd like to just listen from you. How among you are from mechanical engineering or some other branch of engineering? All of you are mechanical?
Mechanical and chemical.
Anybody from the chemical or?
Chemical, madam is from chemistry. She understands
You are from chemistry. Okay.
so she can understand.
From which department?
Chemistry.
From where?
Government college, Jammu.
Jammu, okay. So this may be a little bit interesting to you as well. But as of now, since we have got the diversity in the research areas, so I think it will be much beneficial for the students of all the branches who are interested in taking their research in the field of energy and environment. Okay, because this what I am going to talk in the next hour or so, it will obviously give you the insight into that how we can use different methods for assessment of the energy of different, we can say what waste, if we have got some waste, we have got some biomass or anything of an industrial waste also, how we can assess this through thermodynamical, this TGA we call it, thermogravimetrical analysis. Okay, so the talk will be on energy assessment of pyrolysis of biomass. So we'll be trying to find out how we can use ISO-conversional modeling methods to calculate the kinetic and thermodynamic parameters for determination of these parameters through TGA. Okay, so before I start my presentation, I'll just give you the scenario of the energy and the environment, because those are the two main concerns of the research in the present day world. So, as far as the world energy scenario is concerned, you can see in the slide the energy consumption, the demand, as well as the consumption in terms of fuel. Okay. So, if we see the first slide, this first, we can say this graph here, we can find out the energy consumption of OECD and these non-OECD countries. These are economically, those organized economically concentrated development countries. So we see there has an increase, and if we see the future also we can see the energy consumption is going to increase too much. If we see the area-wise throughout the world, in Africa, Asia, India and China, we can find out the demand of the energy is increasing day by day. By 2040, it will be around from 5 billion, we can say, total equivalent of oil. It will increase to around, we can see 20. So it's around threefold increase in the demand of the energy. Again, if we see the energy consumption in terms of the fuels, so you can see the renewables are getting much more emphasis. These are the renewable energies, or we can say those things which are renewable. The emphasis will be more in the coming years. From you can see from 2010 onwards to 2040, there is much increase in the demand of or the energy consumption of the renewables. So, as far as Indian scenario is concerned, our demand and import of the energy, it's again increasing. From 2005 to 2013, I will take the data. You can find out the total oil consumption has not increased too much. But if we see the demand of imports, isn't it right? The demand of imports is increasing with every year. And if we see the present scenario, for the last decade or so, from 2013 onwards, it has increased twofold. Okay? So this is all about the energy. Okay? The energy demands are increasing, consumptions are increasing. Okay? And our import demands are always increasing. So let me show you another important slide. Now, anybody of you remember this match? It was a match which was played between Sri Lanka and India, and it was pre that COVID time, when we were not exposed to COVID, we were not exposed too much to the use of masks, isn't it right? So, but there was too much of particulate matter in the Delhi atmosphere that the Sri Lankan team was advised by their physios that you should go to the field with the masks on their face. You can see it was in 2017, isn't it right? So it's because of the rising pollution concern. So one is that energy demands and consumption is increasing. On the other hand, you can find out global warming, the emissions of greenhouse effects, and carbon dioxide contributors are increasing. And particularly if we see the India, particularly in the northern region, the particulate matter in the air is too much that people have been advised to go to the certain places with masks on their faces. So it has been found that atmospheric concentration is also increased too much from 316 ppm in 1959 to around 517 ppm, which was recorded on March 2021. Okay. So, what do you conclude from these slides? We conclude that there are two concerns to the present world. Number one is the energy crisis and environmental pollution. These are the two important things. If we see, most of the research is directly or indirectly related with these two things. They are just trying to address these two things, which are presently having, we can say pragmatic, we can say presence in the research areas, the energy as well as environment. Now, there is one solution. The solution is the usage of low-cost biomass, which will not only decrease the demand of the energy and the consumption, and it's a promising option for countering both of these problems, the environment as well as the energy crisis. So how? Why? There are certain reasons. We produce around 10 million metric tons of biomass waste per year in forms of wood, in form of straw, in form of shells and all that. And as per the latest, 1998, one of the papers, it's reported that if this biomass, which is available to us, it is utilized in a proper way, it can reduce around 70 million tons of coal. We can replace this coal by making use of biomass, which can reduce around 160 million tons of carbon dioxide emissions. Not only that, it can generate the employment of around 20 to 30 crore people every year in rural areas. Because usually biomass is concerned with the rural areas. Okay? So the only problem with the biomass is that how to harness this energy, isn't it right? How to harness it, and there should be some sound and scientific management techniques by which we can make use of this biomass. And then there are certain alternative biomass conversion technologies, which has assumed a very, we can say, great importance in present day research areas. Okay, so these are the two things which we have to look upon. Now, of course, all of you, I just want to tell what is the biomass. All of you know, this is the material which is being synthesized through photosynthesis and biological processes. Okay, anything which is being generated through photosynthesis or biological processes, starting with agriculture and forest residues and to the aquatic plants. All of them consist of biomass. This is the most renewable alternate energy source, and it has been found that the total annual production by land and aquatic plants it contributes around 2.6 into 10⁻21 joules, which is almost 10 times what is the present consumption of the world. Okay, that much of energy potential this biomass has. Okay, so why biomass? Why? There are certain reasons for that, because this is evenly distributed throughout the world. Unlike the fossil fuels, we have the fossil fuels which are not uniformly distributed throughout the world. We have certain countries which are having very oil wells also, they are rich, and there are certain countries which are almost dry. They don't have any fossil reservoirs at all. Isn't it right? So this is not the case with the biomass. It's evenly distributed throughout the world. We have these plants and shrubs and valves everywhere. Then its easy processability is another advantage of this biomass. Then it has got almost same characteristics as fossil fuels. Isn't it right? Fossil fuels has mostly what? What is the most abundant part in that is the carbon. Isn't it right? Okay. If we see also it has got the biomass consists of what? Three ingredients. Usually we have got cellulose, hemicellulose and lignin. Isn't it right? Most of them is based on the carbon. Isn't it right? Then it is abundantly available source of energy, and of course, as I already told you, since we are dealing with the increasing pollution levels, so it's an eco-friendly source of energy as well. So it doesn't contribute to carbon dioxide buildup and related problems, because it, instead of giving the carbon dioxide, it fixes the carbon dioxide through photosynthesis. Okay. So let us have a look on the different biomass conversion technologies. As I told you that this is where the technology is used. Okay. Usually we can classify the conversion of this biomass through three different ways. One is biochemical conversion, then thermochemical conversion, and physical conversion. And the biochemical conversion, obviously, there we make use of certain microbes. We make use of either aeration or non-aeration. We usually have aerobic digestion or fermentation, and this can give you the ethanol, which is nowadays one of the blends being used in the fuel. Isn't it right? Bioethanol, you must have heard. Isn't it right? Then CH4, we usually get it through anaerobic digestion. Isn't it right? It's one of the ingredients of the we can say combustible gases, which can give you the very not clean combustion, we cannot say, but it can usually give us a very good heat and energy. Isn't it right? Now, the thermochemical conversion can be further classified under 4 heads. We have got gasification, combustion, liquefaction, and pyrolysis. And gasification obviously gives us the syngas. Syngas is the combination of carbon dioxide and hydrogen. Okay. Combustion obviously gives us directly, it doesn't give us gases, it directly gives us heat and power. Then liquefaction, it gives us little liquid products. Like it can give us it depends on how, which we can say reactions you are going to do with the biomass or its waste. It can give you accordingly those kind of products, liquid products. But I will be focusing on the pyrolysis part. Okay. Now pyrolysis gives us, if you see the product distribution, if you see the product distribution of all the processes, you can find out the most of the products are got through pyrolysis, because pyrolysis gives you 3 products. It gives you gases, condensable and non-condensable gases. Number 2, it can give you the biochar, which is also in the demand, particularly for environmental usage. Okay, bio-oil. This bio-oil is the product from the condensable gases which you can get from the pyrolysis. Then it can be upgraded for particular usage. Isn't it right? There are certain techniques which are used for upgradation of this bio-oil, which can be then further used for different processes. Then the physical conversion is the extraction and densification. Densification, obviously, it's usually called as briquetting. You must have some briquettes of the biomass. Basically, biomass is usually it's not dense. You have to collect it, isn't it right? You have to burn it. Now, if you go for the densification of that, you usually get the briquettes, or which are very densified, isn't it right? You must have seen them in certain countries. Usually, you have seen those hookahs. Hookah आपने कभी देखा ना जो इधर होते हैं usually in those restaurants and all that, isn't it right? So usually they put one pallet of this biomass, which is densified biomass. Usually I have seen it in Turkey. They have usually वहाँ biscuit, जैसे आपके biscuit का pack होता है. Usually they have the packs of these briquettes of this that coal. Usually it is densified and they put it on that hookah for a whole day. They burn it in the morning and it can last up till the evening. Isn't it right? समझ आएगा? So it is the densification of this where you can get some pellets and then extraction. Now extraction is a chemical process where you are making use of certain solvents. You make use of certain solvents. This biomass, how that behaves in that particular solvent. So that solvent extracts certain amount of useful things from it, and those extracts can be used for making biodiesel, for making certain bio-oils, or for making certain, you can say certain oils or creams, which are usually used for these cosmetics and all. Isn't it right? So these are all conversion technologies. By these conversion technologies, we can make use of any of the process to get very best out of this biomass. Okay, but my focus will be the pyrolysis of this biomass and using certain techniques. Okay. Now, what this pyrolysis is? Now, pyrolysis is the thermal decomposition of carbonaceous material in the absence of oxygen. We do not burn it. We just heat it in the absence, because once oxygen is not here, it will not burn. It will not burn. Okay. We make use of heating it. We decompose this biomass under non-oxygen conditions, either in we can say in vacuum or in presence of nitrogen. So here, if this pyrolysis is done and if the water content of the biomass is little bit more, isn't it right? This pyrolysis is then given a different name called a hydrothermal decomposition. Otherwise, it's also the decomposition of the biomass. Okay, but if the water content of the biomass is very high, okay, there is an increase in the vapor pressure of the water. That also has certain constraints related to the decomposition of biomass. Then we usually give that name, pyrolysis, we give it name of hydrothermal decomposition. Okay. Now, basically, it will be surprising for you that pyrolysis is the first step of every combustion. Pyrolysis is the first step of every combustion. Okay. Usually, how it is so? I'll let you know that this is the combustion of the state plate, this any biomass. Now you see, if this is the biomass, isn't it right? The heat goes in. The heat goes in. It's the first step. Now once the heat goes in, what happens? The decomposition reaction takes place within the biomass. अभी तक वो जला नहीं है, वहाँ ऑक्सीजन पहुँचा नहीं. Okay, outer part may burn, but the inner part the decomposition reactions take place, and what happens? There is a transfer of certain mass out of this out of this biomass, which goes out, and then this reacts with oxygen, and the combustion takes place. Okay? It starts, although the time for that will be really less or more, depending on what temperature you are using. Isn't it right? If you are using less temperature, obviously, this process of pyrolysis will take more time. If you are using higher temperatures, obviously, this process of pyrolysis will be in a fraction of a second, but it starts with the pyrolysis. There is a transfer of mass, there is a transfer of gases within the biomass to the outer layer, where it reacts with the oxygen, and we come across what we call the combustion. It then burns up. Okay? So, now, basically, if we see the pyrolysis overall, the pyrolysis process, it's highly complex process, and we do not know much of the chemistry within this pyrolysis, and we try to just assume it through certain means. You are getting my point? Basically, it dries. The first part of this pyrolysis, the drying, it gives us dry fuel. The moisture gets off. Then the primary pyrolysis takes place, where we get certain charge, we get permanent gas, we get some charge. Again, if we further increase the temperature, the secondary pyrolysis takes place, secondary reactions take place. And these secondary reactions can be like, for example, gasification can take place. So decomposition of the material can take place, and further we get tar and we get permanent gases and charge. It can those secondary reactions, they can be reforming, they can be cracking of the material, it can be oxidation, dehydration, polymerization, gasification, water gas shift reaction. All those processes are taking within that biomass. Those processes are taking place when the secondary pyrolysis takes place, and that's why we call it. It's highly complex process. Okay. Now, I hope you are these reactions you may be knowing, isn't it right? Okay. Now, what is the process now? Now, how we can know this? The issue is that how do we observe this pyrolysis now? I told you it's highly complex process, isn't it right? Now, अगर आपके पास कोई complex process है, without assumptions, you cannot conclude anything, isn't it right? We have to assume certain things. Same is the case here. Now, it's a black box. We do not know what is happening inside. Whether it is a gasification process, whether it is a reforming, whether it is polymerization, whatever is happening inside. What we do, we see the inputs and we observe the outputs. Isn't it right? Based on this, we assume what is going inside. Now, that is what we are going to predict, making use of thermogravimetric analysis. Okay, we see what is the type of feedstock, what kind of biomass it is, what are its composition, because biomass from one place to another place always has different composition of carbon, hydrogen, nitrogen, whatever it is. Isn't it right? It's the one biomass is very dense, another is very, you can say, loose. One has got very high heating value, another one has got very less heating value. So we just try to find out what type of feedstock is this. We try to find out the moisture content. We try to find out the particle size, because that's very important as far as the decomposition of materials taking place. If you are going to add certain additives, what is the heating rate? Heating rate means not the temperature. Heating rate means how you are going to increase the temperature once you are going for the pyrolysis. Like it is 10 degrees centigrade per minute, 20 degrees centigrade per minute, 50 degrees centigrade per minute, or 100 degrees centigrade per minute. It's heating rate. And then what is the soak temperature? Soak temperature is related with the water content in the biomass. And what is the residence time? How much time that pyrolysis is going to take place. So what we do, we observe the yield and the properties of the products. So from this, so how do we optimize the pyrolysis and dynamically control the reactions, and we need to understand the kinetics and the mechanism. We try to find out the kinetics and what is the mechanism, probable mechanism taking place through this pyrolysis using certain models. I hope now your picture is very clear to you that why we were going to find out this, okay? Why we are going for TGA and we are going to find the models, okay? Now, how to find the kinetic and thermodynamic parameters during this pyrolysis, okay? So what happens here? So we use the thermogrammetric analysis, TGA. Anybody having exposure to this TGA?
Chemistry, ma'am.
TGA, thermogrammetric analysis, okay? You must be knowing that, okay? So we make use of this data which we are getting from TGA. We try to find out what we call the kinetic triplet. Kinetic triplet में आता है हमारा one activation energy, another one is the brief exponential factor, and what is the order of the rate. We usually predict these three from the TGA method, and the second is the quantitative analysis of the product distribution. Now, product distribution cannot be given by the TGA. Okay, so product distribution is to be done experimentally. So we have the ISO-conversional methods for prediction of this kinetic triplet. From this kinetic triplet, once we are getting the activation energy or frequency factor, we will be able to find out the thermodynamical parameters like what is delta G, delta S, and delta H. What is the change in the enthalpy, change in entropy, and change in free energy in the pyrolysis process through ISO-conversional methods. And then the quantitative analysis of the products is done in a real experiment. We can, if anybody among you is very interested, you can follow me after this this session. We can go to the lab, my lab, and I can demonstrate to you there that how the pyrolysis of the biomass is taking place. Although we cannot run that, there is certain issue with that, but I can demonstrate you the pyrolysis setup which I have already designed myself, and we are making use of that for the quantitative distribution of the pyrolysis. Okay, pyrolysis. Now, coming to this ISO-conversional methods, that's the modeling. How this we can use certain models for prediction of these kinetic triplet, which I already told you. So, basic principle is based on two assumptions. The ISO-conversional models, their basic principles are that the rate of process in the condensed state of the function is a function of temperature and conversion. Or ISO-conversion principle states that the reaction rate or at a constant extent of conversion is only the function of temperature. Okay, so this is the reaction rate. Okay, it's the function of temperature and conversion. Okay, this is why we call at a particular conversion point we have to find a particular temperature. Okay, so what TGA gives you? TGA gives you this data in the form of Excel sheet, isn't it right? What was the basic? We can say I'll just run that also. We'll share that that Excel sheet to you as well, where you can see that how we can. So main thing, the first thing which you have to find out from that Excel sheet, you have to find out the conversion. You have to find out the conversion. Once you are finding the conversion, that conversion will help us to find out the further these temperature will be associated temperature with that. So it will be we can find out the activation energy, pre-exponential factor, and probable mechanism. Okay, so again, you can find out these. There are certain kinetic runs. We find the dependence of time on temperature, time on beta, which beta is the heating rate, on reaction versus or the rate of the reaction versus temperature. At constant fixed temperatures or fixed conversion points, we try to find out that. And these assumptions, then once you get these certain parameters, they are put into particular those. We have the mathematical equations which are being solved, and from those we get the activation energy and pre-exponential factor. I'll just go through that how this is done. Now, as far as the modeling of the biomass pyrolysis is concerned, usually we have got two approaches here. One is the one-step kinetic model, and another one is the multi-step kinetic model. As far as the one-step kinetic models are concerned, they usually represent the conversion of biomass based on the first. We assume the first order reaction here. First order reaction takes place, and we do not take into consideration the secondary reactions which are being taken place within the biomass during the pyrolysis. We take it as the simplest process where the primary reactions take place. The secondary reactions we do not take place. Like for example, I will give you the example of like a biomass. Biomass usually consists of cellulose, hemicellulose, and lignin. Isn't it right? These are the three main components of every biomass. Okay. Now, usually, since these are the three different materials, they are going to behave differently during this atmosphere. Isn't it right? Isn't it right? They are going to behave. But usually we take them as a whole. Cellulose can behave differently, hemicellulose can behave differently, and lignin can behave differently. But for the one-step global-step model, we take them as a whole unit. Whether it is a cellulose, hemicellulose, or lignin, we take it as a biomass. While in the multi-kinetic models, we take them differently. We take them differently, and again we take the average of those, we can say, parameters, then we put them, or we can represent them. Now, as far as the one step, we are going to discuss only the one step global kinetic models here. So, represent the first order reaction, as I already told you, and they usually take this as a one step process. Simplest pyrolysis models are these, and we usually these models do not account for the reaction mechanism. And secondly, the one-step kinetic models, the main advantage of these models is that they are very easy to be adopted, okay, and they give us the direct determination of activation energy, pre-exponential factor, and reaction mechanism. Although it has certain disadvantages that its inability to predict the product distribution हमें नहीं बता सकता कि क्या निकलता है. But that I have told you, we have to go to the lab and try to find out that. Okay. Again, as I already told you, like you can see how the cellulose is one of the ingredients of the biomass. How it goes into the active cellulose, then it gives char here. Again, there are secondary reactions. It gives primary vapors, then secondary char. Again, here volatile chars and char plus low molecular weight volatiles. So this is related to the multi-step kinetic modeling. That these are the things which you are going to ignore, or we are going to assume for that one-step kinetic model. Okay. Now, one-step kinetic models, there's different models which have been proposed by different scientists, different researchers. Based on their name, we usually have very commonly used one-step kinetic model. Kissinger, Akira, Sunrose, we call it KS model. Again, we have got OFW model and Coates-Redfern method. These are the three methods on which I have also worked myself. Okay. Although there are Feldman method, Kissinger model, and many more. Stinnes, Venezovic, and all that. If you can search from this and you can try to find out, you will find around 30 or 40 authors which have given different models. But we'll be discussing these three. Okay, here for how to make use of these models to predict the activation energy or so. Now, here we'll be making use of TGA, thermogrammetric analysis data, to evaluate these kinetic methods. This was first evaluated, it was first used by Coates and Redfern in 1964. They used this TGA method to evaluate the kinetic triplets, and the authors advocated they used a small sample. We usually make use of small samples so that to eliminate the heat effects due to endothermic or exothermic reactions. Whether it's an exothermic reaction, endothermic reaction, depends on a particular biomass which you are going to use, and to maintain a linear rate and accurate temperature measurements. So these were certain assumptions which they use, and they make use of this TGA. Okay. Now, this is how the ISO-conversional model works. Isn't it right? It is based on this reaction, this particular equation, which I already discussed here. The rate of the reaction is proportional to what? Temperature. Isn't it right? It's a function of temperature only. And this temperature is taken in terms of this conversion here. K into 1 minus alpha. Alpha is the conversion. And this conversion is calculated from the TGA data. The main thing is the calculation of this. Now it is W0 minus WT over W0 minus WF. This is the weight, the initial weight, minus the instantaneous weight at a particular temperature, at a particular time, at a particular conversion. So you have to find the conversion, isn't it right? At instantaneous time divided by initial minus the final, which is left at the end, the weight of the sample. From this, we can try to find out the conversion. Okay? Can we go back to that? Anybody can help me? And let me first explain this. Again, we make use of the NNS equation, K equal to K0 exponential minus E by RT, where E is the activation energy, R is the gas constant, and T is the temperature. Isn't it? What is the unknown here? K0 is here unknown, E is unknown, isn't it right? So, making use of these certain mathematical equations and all that, we conclude and we come across these equations, these two equations, which are solved because they do not have the exact solution. They do not have the exact solution. They are solved making use of numerical analysis, generating different iso-conversional methods depending on the approximations used. Like for example, then from these equations we get these three models: Kissinger, Ozawa and OFW, and CR, codes then for the methods. Okay, based on these, once they are solved, based on what numerical methods are using certain assumptions, and we come across, I'll tell you finally, we usually get this equation for KS method. For KS method, I have finally come with the equation. This is the equation of the straight line, isn't it right? This is the equation of the straight line. Is it the equation of straight line? Is it an intercept? Is it an intercept? Isn't it?
Yes, sir.
If you plot left hand side with 1 by T, is the inverse of the temperature. You will get the slope equal to minus E by R, isn't it right? R, you know, is the gas constant, isn't it right? You will give that value of that R, it will directly give you E. What is E? Is the activation energy, isn't it right? So only thing, now what is beta? Beta has been fixed by you while you are doing the experiment. What is the heating rate? Whether you are doing it at 10 degrees centigrade per minute, 20 degrees centigrade per minute, or 30 degrees centigrade per minute. You are getting my point? So it is being fixed. So T square is the at particular alpha. What is the temperature? You will find that from the TGA, isn't it right? And then you will find the slope of the curve. From this slope, you can find out the E. Same is the case with OFW model. You are making Doyle's approximation here to solve that equation. Once that equation is solved, again you get the equation of the straight line. Here, ln beta only. Log of beta, that is heating rate, is plotted against the. No, you have to plot it between the reciprocal of the temperature, 1 by T. It will give you this slope, minus 0.4567, E by R, it will be slope. R, you know, the gas constant, you are getting activation energy, isn't it right? Now, I'll go to the TGA later on. Now, these are the type of slopes you'll get. 1 by T versus ln beta by T square. Here, for OW model, 1 by T versus ln beta. Beta is the heating rate. Isn't it right? So you get at different conversions. So you have, these are the conversions. 0.2, 20%, 30%, 40%, 50, 60, 70, and 80. These are the lines. Isn't it right? From these lines, what you will get? You will get the slope. You will get the slope from, if we energize, you will get the slope, and that slope is to be, if you are going for PS model, you will equate it with E by R. You will slope को multiply करेंगे R से, it will give the activation energy in kilojoules per mole. Again here, we have to make use of that numerical which we found, isn't it right? So I'll try. You just go to the Excel file. I'll just go there. Look, this is one of the data which I am going to share with you. The heating rate here is, it is 10 degrees centigrade per minute. It's the heating rate, beta. Isn't it right? This is the TGA data which you will get. Once you are going for the TGA of any material, you will get the data like this. What is the, and here you can find out, this has been done in the nitrogen. It will be again, it's nitrogen gas. What is the heating rate of that, flow rate of that heating gas? It was, nitrogen, 200 ml per minute. So it is not needed here. But only thing is that it is a pyrolysis and you are doing it under nitrogen atmosphere. Okay. So what is the weight of the sample? What is the weight of the sample? 10.25 mg, milligrams it has been taken. So you are getting the data like this. Time, temperature, okay. At what temperature? What is DTA? TG data. It is given in micrograms. It is given in micrograms. So either you have to change this to the milligrams or that to the micrograms. Because you have to find out the conversion. Now you find the conversion. I will show you. Shall I give this? If you can find out this equation, it is V6. V6 is the initial mass of the sample. जो मैंने अभी बताया 10.24, isn't it right? Into 1000 because I have changed that into microgram minus D31. D31 is this value. It's the mass left at instantaneous mass left. It is W0 minus Wi instantaneous. Divide by. Again, the initial mass minus final mass is 0. Obviously, it went out to be minus. You don't have left anything. So it is also being. So you get the conversion here, isn't it right? So these are the conversions. I have. Now this is 10% conversion. From that, because I have dragged that to all, and I have got the conversion at every point. Among those every points, we have taken 10, 20, 30, 40, 50, 60, 70, and 80. These are the points. Isn't it right? Alpha. And we have to just, what is the temperature? With the increase in the temperature, obviously, conversion is increasing. Isn't it right? With the increase in the temperature in degrees centigrade, this conversion is increasing. So we plot. We do not plot it. We make use of this. Then is temperature का क्या निकालना है हमें? 1 by T. 1 by T. Okay. Okay. So इसका 1 by T जब आपने निकाला, conversion you know. Here we have to find out beta क्या है. For beta by T square, we can find out ln of beta by T square versus 1 by T. जो मैंने आपको अभी दिखाया. And again, ln beta only versus this. You will find the slope, and from that you will find out. Please help me. This is the calculation part. Now you see, this is for KS model. This is 1 by 3 versus ln beta by t square. This is for a particular conversion. Point 2. These are the 3 heating. I have taken 4 heating rates. I have taken 4 heating rates. 5 degrees centigrade per minute, 20, 35 and 50. For all the 3, I calculated this, and you can find out beta t square for OFW. I got it, all those points, isn't it right? Then we plotted it. And from at the bottom, is it visible to you? Huh? Now you can find from PS model. These are the conversion points, point 8 to point 2. Isn't it right? This is the average of this. 119 kilojoules per mole. From OFW model, we get 126. So there is a difference of around, because both equations may differentiate. आपने वो देखा. So our these then again I am trying to find out the A. A is the pre-exponential factor. Isn't it right? Again, then you can plot them. What is the activation? How activation energy changes with conversion? So it's not fixed, or it is not generalized. For every biomass, it is different. Activation energy can sometimes increase, it can then further decrease, it can again increase, or it can have certain trend. Okay, so we try to find out the trends. The conversion versus pre-exponential factor. Again, it can have certain trends, and you can then plot them. Okay, is it fine? Then this is the order of the reaction. Again, calculation of R. Then for 5, 20, and 35, these are okay. Now for thermodynamical parameters, once you are calculating, once you are done with this, okay, I was here. As far as PPT was concerned. So you can find out from this. We can try to find out. We can find out the activation energy and pre-exponential factor. Okay. Again, coming to another part. Another part was the Coates-Redfern method. Coates-Redfern method is little bit. We can say it can give the probable mechanism which is being followed by this pyrolysis method. Okay. Since so this Coates-Redfern method is also based on this, but here जो हमारी जो ये है ना equation, इसमें हमें ये G alpha आता है. It's not beta here. Earlier it was beta in KSN or Weber model. This here it comes G alpha. Now G alpha is then predicted through this integral. Okay, where you can take n equal to 1. Alpha, if you take a particular conversion point, 0.3, it will be 0.3, and 1 minus alpha will be 0.7. Once that is there, यहाँ आपको एक numerical आ गया, K0 you know, these you know, and you can find out value of G alpha. Okay? So what I mean to say is that on the basis of this G alpha, what values you are going to give, there are some predetermined mechanisms. For that, values of this integral can be given as alpha, 1 minus this or so, and accordingly we can predict this kind of mechanism being followed by a particular pyrolysis method. Okay, I told you it's a black box, so many things are there. No, but again, based on this, we can predict what is the most probable mechanism which can be followed by a particular pyrolysis method. So R1, R2, R3, these are diffusion-based methods. This is chemical reaction-based method. This is the contacting geometry-based methods, depending on what values which you are going to give to that integral. Okay, G alpha. So again, here we plot ln G alpha by t square versus 1 by t, and we get different models. We get different slopes or different these. Again, among them, then we see what is the value of activation energy and pre-exponential factor among all this, which matches our values from KS and OFW model. So it matches mostly with F3 and DF, as far as my case is concerned. Okay? So we presume that the predict, or we can say the mechanism which is being followed by this pyrolysis method is based on F3, order of the reaction, or and the diffusion method based on D5. Okay? So I'll take up now my research work which I had done during my PhD. I took 4 biomasses which are commonly available in our Kashmir. One was the willow shavings, wood shavings. Usually we have the bad industry in Kashmir which makes use of willow. We have got English willow and Kashmiri willow, isn't it right? Bad, bad. So we have lot of waste generates there in terms of shavings when they are being finished. Okay? So I took that sawdust and I took that shavings, made that again the deodar, which is one of the basic material which is being used for the furniture here or for making houses and all that earlier. It was one of the for making timber. Timber ke liye I used this sawdust of this. Then again I did walnut shells. Again we have got a large production of walnut shells in Kashmir. I took these shells, uska jo biomass waste hai, then almond ke shells. So these were my 4 biomasses which I took, and we try to find out after pyrolysis how they are going to behave. What will be the product distribution? मैंने नहीं किया. Only I did one of our now research. My research scholars are doing certain works on it. Again, as far as the product distribution is concerned, I only focused on ISO-conversional methods or to TGA methods to find out the activation energies and all those parameters and predict that how they are going to behave if they are pyrolyzed different ways and what is their biological or we can say bioenergy potential. So these were the analysis which were done on these 4 biomasses. We went with approximate analysis, ultimate analysis we did. Then I did the bulk density test, angle of repose, heating values. I tried to find out. You know how this empirical formula can be found out for a particular biomass? Anybody having this idea? How you can find out this empirical value or empirical formula for a particular biomass? Right? For this empirical formula is for, I think it is for willow wood. Isn't it right? Waste. Huh? So it is CH. So you have to simply find once you have got this CHNO analysis, CHNS analysis. आपने करते होंगे, isn't it right? करते हैं ना? So उससे आपको क्या लेना है? You have to find out H/C ratio and O/C ratio. Once you are done with this, isn't it right? So आपको फिर molecular weight से divide करना है. You can find the number of moles. You take C as 1 and particularly एक कितना निकलता है आपको? Accordingly you can fix an empirical formula of a particular biomass, whatever you are using. You have got my point. Okay. So this was for walnut shells and all that. This was the equation which was used by me for predicting the heating value. So if you don't have the facility of getting the heating value, you can predict the heating value based on the proximate analysis of the variable. Proximate analysis is very easy to find out. If you have the furnace, you can find out what is the ash content, what is the volatile matter, what is we can say fixed carbon. Fixed carbon is found by decreasing, or we can say by differentiating this ash, volatile matter and that from 100, we will get the fixed carbon. Like for example, fixed carbon we have not calculated. We have calculated ash, moisture and volatile matter. Isko 100 se minus karo, so you will get fixed carbon. Okay. So from this you can find out if you give this value to this equation, it has already been you can say tested for around 500, more than 500 samples. So it has very less that error. Okay, so you can directly use this for predict the heating value. Okay. Then FTIR was done. Obviously, mechanical people will be much more aware of this technique. We try to find out what are the functional groups. This was only the characterization part. So I have the FTIR in my lab. You can come, whosoever is interested. We can give you the demonstration of that as well. Then I did some chem to find out what are the morphological, we can say, differences in these 4 biomasses which we have selected. I think I am not exceeding my time. Huh? No. Okay. So these are the TGA data which was plotted. The TGA data हमारा था, which we plotted here. So that was at different heating rates, at 3 heating rates. Then this is how to find out the stages. I did जो आपका TGA data है, एक तो हमने उसमें conversion निकाला. If will temperature versus TGA. So this is the graph, okay, and this is complete DTG. It's a differential change in the mass. It's a differential blue line. Differential change in the mass with respect to temperature, okay. So you can just हमने इसको 3 zones में फिर divide किया. First zone, second zone, and third zone. First zone में little bit there is less decomposition, and most of the decomposition is taking place in the second zone. In the temperature range between 500 to around 650. That's why we have given. And what is the heating rate? At different heating rates it is different. And what is the conversion? How much it's changing? So you can either predict it like this separately. In one of the papers, I have predicted it separately for 3 heating rates. Isn't it right? For in another paper, I have predicted it in a same graph. Depending on how you are going to do it. Okay, it is for 10, 25 and 50 degree Kelvin per minute. Earlier it was separate for 3. So depending on how you are going to show it, then again we go for finding out the different these zones of this decomposition. Then you can find out this DSC. Differential scanning calorimetry, isn't it right? It says us how physically, with respect to temperature and time, your sample deteriorates. Okay, how it's going to affect that, isn't it right? That is how we have found it for 4 at 3 heating rates. Again, it depends on the heating rate, isn't it right? So we have done it for 3 heating rates, and these are the graphs which we have got. So this was the through PS model. You can find out. We have found out the average of this activation energy as 124. Here we have got average at 128. By OFW model for DS, I will go directly to. Again, it is for DSD. That was sawdust, Judar sawdust. This is for walnut shell. So you can find these values are different for all the 3, isn't it right? So later on, then I have concluded my results like this for 4 these biomasses. So you can see that how this activation energy through KS model changes. Okay, delta G. I have missed one of the slides probably, where you can find out the thermodynamic. Yeah, this one. I told you that from PGA, how can we find the triplets? Activation energy, the pre-exponential factoring mechanism. So now from that, you can find out delta H simply. Delta H is equal to E minus RT. R, you know, isn't it right? You have to change, you know at a particular conversion point what is E. You have to find out the average temperature. Okay? And here, this temperature, you cannot find out average. You have to take DTG curve, जो है, उसमें जो maximum temperature होता है. The maximum temperature from the DTG curve, you can put it that value here, and it will give you directly this delta H and delta G again. E is the parameter which I already know. Okay. TP, I already write. TP is the peak temperature of the DTG curve. Here. KB, Boltzmann constant, H is Planck's constant. Okay, you can verify these equations. Okay, you can find out delta G, the delta S. Obviously, once delta H and delta G is there, you will find out. Again, you only know unknown is the TP. Is the okay? So what if these are the thermodynamical parameters? The basic thing was once you are done with main thing is to find out the activation energy. Once from activation energy, you can find out these things. Okay? I had missed out this. So this was the conclusion. You can find out how the pillars are different. It's the different values of activation energy and delta G, delta H, and delta S. So you can find out while comparing the values, you can find out this has got very high potential of the Deodat stardust. If we compare the 3, 4, it has got very high potential of bioenergy. It's too compact. अगर हम ऐसे भी देखेंगे, इसकी compaction बहुत ज़्यादा होती है, isn't it right? Its density is more as compared to others. Okay, so we found that we try to find out the activation energy. It progressively changes with the conversion. Okay, the another this conclusion what it confirmed that pyrolysis is a highly complex process, and with the rapid increase in the activation energy, with the conversion, it is indicative of initiation of main process of pyrolysis because of those different stages. Okay, so decline in the energy later indicates the gradual transition from one reaction method to another reaction method. देखिए अगर आप देखेंगे ये है ना activation energy changes then, isn't it right? There are different rules, but it is because of the different reaction mechanism. I told you the reaction mechanism are based on gasification, polymerization, reforming. You don't know what is happening inside, isn't it right? So there is a gradual change from one mechanism to another mechanism, and then we have predicted the values based on the chemical reaction and the multidimensional diffusion model P5 and F3, which were very, very close to the mechanism which is followed by these parameters, these we can say biomasses. Okay, so this is the list of publications which is based on this. Okay, I have got around 5 or 6 publications which are only based on this these methods. And recently in 2023, I got one publication. It has got impact factor of 7.616 in sustainable energy technologies advancements. It was the co-pyrolysis of petroleum coke and wood pellets. It was a co-pyrolysis. We made use of 2 things: pet coke and wood pellets. Okay, and prediction was same. Process is only thing is, जो भी मेरी if you go through my publication, you can try to find out. I have only changed the biomass. Biomass. That is the novelty of my work. The rest of the works are almost same. But how do you present them so that it's not caught in the plagiarism? I told you that you can predict your results in different ways. Sometimes you can have different. लेकिन मैं आपको कुछ tricks बता रहा हूँ ना, isn't it right? Let us come to that part also, because that is what we usually focus on as a researcher, isn't it right? Like for example, आपने एक graph दिखाया where I saw all the 3 heating rates in one graph, isn't it right? You can put it another way. I put them 3 heating rates under 3 different. Then again you have to then predict the things and all that. So thank you very much for your attention. If anybody has any question, yes, please. Yes.
जब वो उससे तो इफेक्ट पड़ता है ना,
yes.
तो हम कैसे प्रेडिक्ट करें कि जो मतलब जो प्रोडक्ट्स हैं वो कैसे हमें मिलेंगे, क्योंकि डिकम्पोजिशन किस स्टेज पे क्या क्या हुई, क्योंकि वो सारा टर्म चेंज होता है.
I told you na that if you can only predict the pyrolysis. देखो. If you were attentive here, I told you, we just see the yield and the properties, isn't it right? And we can just see the effects of these things on these. What is happening inside, we don't know, isn't it right? Now, if you want to see the real products, how they are going to affect your yield. Isn't it right? You have to go experimentally, you have to do it. There you can change the heating rate, and accordingly you can see how the yield is changing, how your products are changing. You can sometimes get very good amount of biochar at low heating rate. But at high heating rate, your biochar will be less and your bio oil will be more. Okay, I have not taken that thing into consideration. I think it's okay for you. And again, I told you if you are allow free this time, you can come and I can show you the real experiment how we are doing. Any other questions, please? You can again reach me at my email. It's already there. Okay. If anybody has, we are here only for you. Our Tommy here, and you can reach me at this turbomachinery.ac.in. Thank you very much again for giving me an opportunity to discuss.
Thank you very much, sir, for such an informative session.
So,
Now
I'm
I would like
inviting
to-
Dr. Muslim Sahab to come state Tanveer Sahab. So, thank you, sir. May God bless you. I think on day 2, our Honorable Director delivered a speech on National Education Policy 2020. So, Dr. Muslim, he is Associate Dean of academic section. So, he will tell you what is the status of how far we have done in this thing, NEP 22, how much we have implemented in our institute. So, Dr. Muslim.
Now, you already had a detailed discussion on national education policy. We have BTech students over here. Okay. Now, regarding the implementation part, I don't need it. Regarding the implementation part, our BTech program currently has require minimum 180 credits to pass a course or program. Am I clear? 180 credits. And maximum is 200. Now, if any student earns at least 40% of the credits, 40%, he will be given, suppose he wants to leave, he will be given a certificate in mechanical engineering or certificate in civil engineering. He has earned 40% of the credits at least. Am I clear? If it is more than 40% but less than 55%, I think this is clear. Now, if he has earned at least 50% of 55% of the credits but less than 70%, he will get a mechanical in, say, for example, chemical engineering or mechanical in mechanical engineering. Diploma in mechanical engineering. First thing was that 40% of the minimum total minimum credits required for BTech program. That means 40% of 180. Am I clear? He will get a certificate in mechanical engineering. He has earned 55% but less than 75%. He'll get diploma in mechanical, chemical or civil engineering. Clear? Now, if he has earned more than 70% of the total minimum credits required for a BTech program, he'll get advanced diploma in, say, mechanical engineering. Is this clear? Now, regarding second part, suppose a student comes back, I have to join back. Clear? The minimum gap, he has to take 2 academic sessions. That means he can come back only after 2 semesters. If he comes back immediately, say for example after 10 days, 1 month, 2 months, 3 months, he has to surrender the original certificate that has been issued, a diploma or a certificate or advanced diploma. Am I clear? He has to surrender that, and only then he will be admitted back. And in addition, there is second criteria that he has to complete his BTech program, including the gap, in a maximum of 8 years. It cannot be 8 years and 1 day. It has to be within those 8 years. Am I clear? Any confusion regarding BTech program?
No, sir.
Clear? You can come back, you can take an exit, you will get those certificates, but there are certain limitations. Now, regarding the MTech students, we have MTech students as well.
Sir, is this applicable for the existing
It
batches?
is applicable for the existing batches as well. It has been applied retrospectively. Suppose we have a student who has left previously in some year, 2000, he has left, it will be given to him as well. Regarding BTech, it is being applied retrospectively. Am I clear?
Yes.
Now this is clear, you have to complete, if you come back, you have to complete within 8 years. Maximum limit is 8 years. And if you want to get both the certificates, BTech as well as some other intermediate exit certificate, you need to have a joining gap of 1 year, 2 academic semesters. Am I clear? Now regarding MTech students, If an MTech student who has joined this institute for an MTech program, he wants to take an exit, but he has earned more than 50% but less than 100%. He'll get a PG diploma in, say, for example, thermal engineering, PG program in mechanical system design, and so on and so forth. What are the programs? Is this clear? Now, regarding PhD, if a student under fellowship or without fellowship, we have self-finance case, we have fellowship students, all those cases. They can take an exit. If they take an exit, he has been in the program for at least 4 semesters. So I'm talking of MTech. He has earned successfully 10 credits, and he has published one research paper in Scopus or SCI, and that should not be a review paper. Am I clear? That should be from his work. He will be given MS by research in, say, mechanical engineering, MS by research in chemical engineering, and so on. Is this clear? Now, suppose he wants to come back. He wants to come back. Again, the criteria is that he has to take a gap of 2 academic semesters. If he joins back, he will have to publish 2 fresh papers. Clear? That previous one will not be counted because he has taken a certificate for that. This is all we have implemented. No, you don't need. If he again joins with before 2 academic semesters, then he has to submit. If he joins after, that is valid for MTech and BTech as well. If he joins after 2 semesters, he doesn't have to surrender that certificate. Am I clear? Is this clear? Now, regarding a student, and here, suppose he was on fellowship. Fellowship will not be given to him after 2 if he joins back. Clear? Fellowship, no, fellowship will not be there. अगर वो fellowship वाला student था, उसने exit ले लिया, वापस आ रहा है, fellowship खत्म. Clear? He will get MS by research, 1 research paper, and there's a fresh criteria that he has to submit. He has to have 2 fresh papers, research papers. Clear? And again, those should not be of review papers. Clear? Now, regarding BTech, we have not decided anything. Suppose a BTech student joins a PhD program. That is still in abeyance.
Sure.
It's safe, it's safe. For this, you want an exit for a PhD program or PhD. That is not a part of NEP. That is already there. Suppose there's a transfer of credits. That is taken care separately. Suppose we have students who have joined, who were enrolled in, say, IIT Delhi. They have left their PhD there. They have come to join IIT Srinagar. They have transferred their credits to IIT Srinagar. Now they have to pass only one course, that is the research methodology. Clear? Rest of the credits are taken care of. They are transferred from one institute to another institute. Clear? That was already existing in our institute. कोई confusion है इसमें exit policy में? Is this clear? Clear? Thank you. This is all I have to say regarding this.
Now I would like to request Dr. Tanvir Rasam to please take a motion, sir. Thank you very much, sir, for such an informative session.
You join me at the environmental lab as my scholars have been. Yes. As you wish. Environmental lab, we have already, I have already told them that we set up functional, you can go and see them, okay? My scholars at the environmental lab in the ground floor of chemical engineering. Okay?
We have an expert and the session starts at 2 p.m.
Queries also you can just
and she is an energy researcher specializing in hydrogen battery storage. She has done BTech and his master's in mechanical engineering of thermodynamic, respectively from PNU Erosion. Her PhD was from IIT Bombay, where she worked on heat transfer design of large-scale hydrogen storage systems. She is currently working as an assistant professor in the Department of Mechanical Engineering, IUST. She was also worked in Mechanical Department in Kinetic Srinagar as a faculty from 2014 to 15. Today she will be taking about the solid-state hydrogen storage systems and giving an overview of materials and systems. Now I would like to welcome the speaker on the dais to deliver the lecture.
Assalamualaikum and a very good afternoon everyone. I'm Mohammed Shafzal and I'm currently Assistant Professor at Islamic University of Science and Technology. As the speaker introduced me, I have previously worked here and I'm really happy to be here and see some familiar faces from before. So I'm very happy to be here, so I'll just start right away with the topic. So hydrogen storage, characterization of hydrogen storage materials. That's what I'm going to talk about today. But before I start, I would like to let's just talk briefly about hydrogen energy. You might have all heard about how major investments are going on for clean energy. There is a lot of effort globally to reduce the carbon dioxide emissions, right? So this is only possible when we switch drastically to renewable energy. Now, considering solar energy, wind energy, all of these of course exist and are very much a part of the renewable energy scenario. But if we want an energy carrier, a reliable energy carrier that can help us use energy when we need it. For example, if we talk about solar energy, we have in some months we will not have the same insolation as we have in the other months. Similarly, in case of wind, it is something which is not really in our control. So if we want an energy carrier, some way to store this energy, hydrogen can be that vector on that carrier. So today in my talk I'll discuss at length how it is, but just to give you a brief idea about the carbon dioxide emission scenario currently in the across the world. If you see that in developing countries, especially like India and other countries also, you can see developed countries have started, that shift towards renewable sector heavily. But in developing countries or which are currently experiencing rapid strides in their economies, such as China or India or even for that matter Brazil, these countries are still are experiencing increasing carbon dioxide emissions. So overall you can see that around the top 10% emitters emit 67.6% of carbon dioxide emissions. So if these countries were to switch to a cleaner alternative to fossil fuels, we would be the greenhouse emissions or the climate change that is imminent would be taken care of. So that means what I'm basically trying to emphasize is that hydrogen energy could be an answer to a non-greenhouse energy structure basically. So how does the hydrogen energy structure work? So basically, first I'll talk about why hydrogen is the answer. So first of all, it has a very high calorific value. There are no toxic byproducts involved, and it is easily available. Although this could be placed in asterisk, I'll talk about that a bit later. But so coming to the high calorific value, hydrogen energy has a calorific value which is around 3 times that of petrol or diesel. So that is like really huge. And also the fact that there are no toxic byproducts. If we have to subject hydrogen to combustion or even to heat pump for the fuel cell routes, in both the cases the byproducts are water, right? So that means the have. So first of all, we can have hydrogen from renewable sources being produced, and this is be stored and distributed, and then finally it can be sent for application for mobile purposes or for residential or commercial establishments. Now, what actually happens is that hydrogen is stored in tanks. Currently, that is what is in vogue. Hydrogen is stored in the form of compressed gas in tanks, and this compressed gas is supplied to a fuel cell, which in turn produces electricity, which is used to power your vehicle or your residential establishments. Okay? So that is how it operates. Now, this is again schematic of how electrolysis is done, and then hydrogen is stored and distributed, and then finally it is sent to the fuel cell for application. So as you can see that it is a research area where research has to be done on three fronts. One is the production of hydrogen, the other is the storage and distribution, and finally the application. And all these are three separate entities in which we have to, research is done in separate ways. So now today I'll talk about hydrogen storage and distribution. Now you're all aware that hydrogen is the lightest element, right? So with a density of around 0.08 kg per meter cube at normal atmospheric conditions, it is, if I were to store 1 kg of hydrogen, I would probably need a space as big as the washroom in my house. Just to give you an assessment. Around 11 meter cube. Okay, so that's roughly हमारे घर पे छोटा स्टोर या वॉशरूम होता है around that. Okay, so in fact उसे थोड़ा कम, but roughly that. So can you imagine storing 1 kg of hydrogen in that? Now, obviously we can't afford that bigger space. So if we want to carry it around for whatever use, we have to be able to store it in a smaller space because density is very low. So now we have three methods. Either we can go for compressed gas storage, which involves storing hydrogen at a pressure of around 700 bar, which is a lot of pressure at 20 degrees Celsius. Then we can also store it in the form of a liquefied hydrogen storage, which occurs at minus 253 degrees Celsius. And the third method that we have is storing it in the form of a hydride, which can be done at 20 bar and 20 degrees Celsius. I mean, it can be different for different alloys or metals, but this is just a reference number. It can be done at atmospheric pressure or slightly higher than. Like when you compare 20 bar and 700 bar, you can see that 20 bar is slightly higher, correct? 700 bar is very huge. So these are three methods that we have. Now coming to compressed gas hydrogen storage. As you can see, compressed gas hydrogen, whereas it's 700 bar, it can also be stored at a lesser pressure. It's not necessary that we have to store it at 700 bar. So basically, we have four types of storage tanks for compressed gas hydrogen. One, we can store it in a one tank, which consists of a simple metal cylinder in which it can be stored. Obviously, the thickness etc. is taken care of, but it can hold pressures up to 100 bar. Okay. Then you have the type 2, in which case you have a metal body, but it has a composite lining inside. Actually, what happens? Hydrogen is a very corrosive molecule. It can, react with the metal container, and it can penetrate through the cylinder. So that is why this type 2 tank is designed, and it has a composite liner with it. Now, as you can see, the gravimetric capacity is higher. Gravimetric capacity is an indicator of how much hydrogen can be stored in a tank. Basically, gravimetric capacity is how much hydrogen can be stored in per kg of tank. Because tank का भी कुछ weight होगा, it has its own weight, right? So that means here you have 2.1 kg hydrogen, which is slightly higher than type 1, which means that you're basically pressurizing the hydrogen more. Because that is the only way you can store more hydrogen, right? Then type 3 is we have a metal liner and it has a composite overlap. So you use resins to cover the surface of the liner, the metal tank. So in that way it imparts more strength to the tank. So again, this will have a high gravimetric capacity. So Toyota came up with this type 4 tank, and they said that the gravimetric capacity capacity that they achieved was 5.7. So in this case, what we have, we have a composite body and it has a composite liner. It is carbon fiber reinforced and very strong. So you can imagine that it will be subjected to longitudinal stresses also and fluid stresses also. So we have to ensure that it is designed on the lines of a pressure vessel. Okay, so it has to withstand that. So of course, the cost factor is there. It is $633 per kg, which is like around money. So this is just an idea about if we were to run a car, okay, 4 kg of hydrogen would actually be required for that. It doesn't normally have tank where you have a full tank. That would be around 30 kg of petrol if I talk about my car, a normal hatchback. Okay, so that's like 30 kg of petrol. So we can do that in 4 kg of hydrogen. Okay, so if we want to store this, we would have to use 7 type 1 tanks. Okay, we would have to use 3.5 type 2 tanks and one of each. ये एक एक चल जाएगा. That's one, the type 3 and type 4. So you can see that we can't run around with 7 cylinders in our car, right? We have to pressurize it and we have to find out alternate methods of storing hydrogen. Now, like I said, Toyota did come up with this composite liner and composite body, and it's working fine. Thermodynamic is working absolutely fine on this. But the catch here is that if you want to compress hydrogen to 700 bar, you are spending a lot of energy in compressing it. So basically, that is a lot of energy penalty. So if you make like 100, say megajoules, say for example, let's say if you make 100 megajoules of energy out of it, 40 megajoules you have to spend it compressing it. So we are paying a huge penalty in terms of the energy to compress it. Not to mention the fact that the tanks are very costly. So that is why we have to look for other methods as well. Now we also have liquefied hydrogen. Hydrogen can be stored. Is there some issue here? So now we can also store hydrogen in the form of a liquid at minus 253 degrees Celsius. Now you can imagine that also. Like reducing the temperature to minus 253 degrees Celsius, that is a lot of cooling power, right? So again, we are taking a lot of energy penalty here, and then there is also boil off. What happens, like I said, hydrogen is a small molecule, it has a tendency to escape. So if it escapes, the vapor pressure in the tank drops. To stabilize it, more of the hydrogen vaporizes. That means we are losing out on hydrogen. Okay, and this boil off happens continuously. So we can't afford for that as well. Also, one thing that we have to take care of when we are using liquefied hydrogen is that the design of tanks is governed by minimizing heat loss and not the maximum allowable pressure. Because here we don't store hydrogen at high pressure, rather we store it at a low temperature. So that means the design is governed by heat transfer rather than the strength of materials. I hope that is clear. So next we have the solid state hydrogen storage. Now, when we talk about solid state hydrogen storage, we do have an interesting method of storing hydrogen, where we can cause hydrogen to react with a metal, okay, and it will form a solid. Okay, so now we don't have gas, we don't have to worry about leakages or anything. Okay, so now it has formed a compound metal hydride and it gets stored in that form. We can also have chemical hydrides, radioorganic frameworks, carbon nanotubes, in which we can store hydrogen. But the issue with all of these is cyclability. Right? You can store hydrogen, but then you also have to get it back. It's not good enough that a material stores hydrogen. It also has to release it equally easily. Right? And in case of radioorganic frameworks or in case of your carbon nanotubes, the storage happens at temperatures like 77 Kelvin. I mean, how are you going to go and reduce the temperature to 77 Kelvin if we want to make it practical? Right? So we need to look for materials in which hydrogen can be absorbed at moderate operating pressures and temperatures. Let's actually quickly along and highlight the way. We can have either simple type hydrides. For example, hydrogen can form a bond with magnesium and it will form a magnesium hydride. Then it can also form a bond with something like LaMi5. Okay, so now here LaMi5 then and form a hydride. This is again an alloy. So these are known as intermetallics, and they can be of the form AB5, AB2, A2B, and AB. Okay, so AB is, for example, PiFe, when Pi is titanium is A, and Fe is B, and hydrogen is, of course, H2. Then again, zirconium vanadium, we have zirconium is A, vanadium is B, and then you have hydrogen. Same is the case with LaNi5, lanthanum is A, nickel is B, and then you have hydrogen. So the thing about these intermetallics is they have a very interesting property. Now, some of the materials, when they react with hydrogen, they form a very stable hydride. So it is very difficult to get hydrogen back from it. That means if you want the hydrogen back, you have to supply a lot of heat, okay, or reduce the pressure a lot, so that the hydrogen, is, so that the material is dehydrogenated. But on the other hand, if we use these intermetallics, we can solve this problem. How? Let's take the case of zirconium vanadium. Zirconium forms a stable hydride, but its capacity of storing is very low. It does not store a lot of hydrogen. On the other hand, vanadium has a very high storage capacity, but the hydride is not stable. So what we do is we form an alloy of the two and allow hydrogen to react with it. So this solves the problem of instability also, and the fact that we have a better storage capacity as well. So if you take a look at these, some of the alloys in which hydrogen has been stored, and it is the gravimetric density, that is amount of hydrogen, kilogram of hydrogen per kilogram of, per 100 kilogram of the alloy. So here you can see, let's take the case of PIFE. So it is around, how much? 1.8 weight percent. So that means 1.8 kg of hydrogen can be stored in 100 kg of TIFE. Now that is not a lot of hydrogen. I mean, if you think about it, 8 kilo stored करते हैं या 2 kilo stored करते हैं 100 kg में, that's not a lot. But you also have to consider that hydrogen has a very high calorific volume, so that 1.8 kg of hydrogen can actually go a long way, right? So yeah. So now if we want to design a hydrogen storage system, how? Again, this is okay. So if we want to design a hydrogen storage system, how do we go about it? First of all, we need to know what are we designing the system for, how much output are we requiring, and this has to take into account the fuel cell efficiency. What I mean by that is, suppose if you need a system for, say, if you need a 5 kilowatt system for 2 hours, okay? You need 5 kilowatt system for 2 hours. So that means 10 kilowatt hour system is required. Now the fuel cell might have an efficiency of say 50%. Okay? So that means you have to design hydrogen storage system for 20 kilowatt hour. Right? So now that you know the output required, which is say 20 kilowatt hour, now you have to take into consideration system size constraints. What that means is, if I'm using it for say some vehicular purposes, some mobile applications, okay? In that case, I need to ensure that it has the least possible size. Gravimetric capacity of the alloy should be the highest possible, so that I don't have to calculate a bulky system. Whereas on the other hand, if it is for stationary purposes, then I don't need to really worry about that. It can be a bit long also, large also. But we also have to take into account that it should be this high, like LPG gas cylinder, okay? It is something which has been designed keeping in view that it should fit into a normal kitchen, right? It is easy to transport also, it's not too large. Whereas if you see the oxygen cylinders that are used in hospitals, they are very long. Imagine if we were to use something like that in our houses for kitchens, it would be difficult to maintain, right? So so to say, the ergonomics also have to be kept into mind. Then we also have to select the gravimetric capacity of the alloy accordingly. Like if we are using it for the material applications, we will try to use as high as possible the gravimetric capacity. Then the operating temperature and pressure. So for example, if I were to use the initial hydride, it has an operating temperature of around 300 degrees Celsius, which is not always possible. Because I might not be, it might not be easy for me to attain, so I might not go for that. Instead, I could go for, say, like I have personally worked with lanthanum cerium nickel. It works absolutely fine at 25 degrees Celsius, and a pressure of 80 bar is more than enough It will be absolutely fine, as you will see. So, yeah, so then we go about the alloy selection, verification, activation, and finally we do the performance studies. The activation, the alloy has an oxide layer on top which blocks the reaction sites. So it has to be heated and it has to be subjected to a very low pressure to break off that oxide layer. And that process is called activation. So now that we have the alloy, we want to find out how much hydrogen it stores. Okay, how much hydrogen an alloy stores. So we will take a fixed quantity of the alloy. Okay, we will take a fixed quantity of the alloy and we will place it in the reactor. We know say 1 gram metric per gram, we will place that in the small reactor. In the standard volume, we will allow hydrogen to go into the standard volume. Now standard volume is something, is common volume for double. Say for example 350 cc or 500 cc. So we already know the volume of this vessel here. So we allow hydrogen at a certain pressure to go into the standard volume, and we close. This valve is also closed. This valve is also closed. It's just allowed to go inside. So the pressure again is noted. We know the pressure of this gas. And what happens after that? We evacuate this entire system, the rest of it, except this cell. Now, then what we do is, we allow hydrogen to go to, we close this, we allow hydrogen to move into the reactor. Okay, now that the hydrogen has moved into the reactor, what happens is that the pressure will start dropping. Now when the pressure starts dropping, because the hydrogen is being absorbed by the system, right? So the pressure will start dropping. So once we after a certain interval, we will see that the pressure has stabilized. It is not dropping anymore. So that will be our final pressure, P2. Since we know the volumes, right? We know the standard volume, we know the volume of the tubing and all. So we can find out the number of moles of hydrogen in the first case and in the second case. So the difference between the two will be what? The hydrogen that has been absorbed by the system. So this is what the process looks like when it's plotted. So in this case, you can see that we are supplying hydrogen to the system. The pressure is increasing. Okay, and after a certain interval, it will become constant because it has reached an equilibrium. Okay, so then finally we have an increasing pressure again. Okay, so here we have only say alpha phase. Here we have alpha plus beta phase, and here we have only beta phase. So this will give us the reversible capacity of the system. As you can see, there will obviously be hysteresis also involved. I think those who have taught might recall the previous diagram for water. I don't know, I really used to enjoy studying, that Steve and to have the rapid reaction or rapid absorption of hydrogen within the system or absorption of hydrogen within the system, we need to ensure that the temperature within the system is maintained. Because suppose if I am supplying the supply pressure is say 80 bar, okay, I start out at 95 degrees Celsius and the equilibrium pressure at 25 degrees Celsius, let's just say for example it's 5 bar. Okay, so currently I'm operating with a pressure difference of 75 bar. So the reaction rate is going to be fast. But what happens is that the metal hydride formation reaction or the hydrogenation reaction is an exothermic reaction. Okay, so this releases a lot of heat as the metal hydride is formed. So if I do not evacuate this heat or withdraw this heat from the system, it increases the temperature of the system and hence the equilibrium pressure. So now we started out with the equilibrium pressure of 5 bar. Now if your equilibrium pressure reaches 15 bar, so that means the difference between the supply pressure and the equilibrium pressure has reduced, the driving potential for the reaction has reduced, so the reaction rate will reduce. So it is imperative that we design a heat transfer system for the storage system as well. Now, if we see that how can we enhance the heat transfer in any system, we can either increase the thermal conductivity, we can either increase the heat transfer area, or we can increase the heat transfer coefficient. Right? Fundamentally, two main चीजें कर सकते हैं. So if we talk about thermal conductivity, what we have seen is that in most systems to increase thermal conductivity, we use metal foam, okay, or we can also use expanded natural graphite. Both these things, we can also use metal shavings, other things, right? They also help, increase the effective thermal conductivity. But these are when foams are effective. Expanded natural graphite has been used a lot. So then, if we want to increase the heat transfer area, we can add fins to the system, we can add cooling tubes. If we want to increase the overall heat transfer coefficient, so what we can do is we can add a water jacket to the system, or we can just place it in a modular water tank. We can do that as well, right? So because obviously water has a high heat transfer coefficient than if you subject it to free convection in air, right? So that means you would have a better heat transfer, right? So if we look at the studies with, you have to get an order. Yeah. Okay, I'll get it. I think this is for the lag. I guess I just need to be more patient. So if we look at the percentage of studies with different heat transfer techniques, we see that by and large, most people have used either a cooling fluid jacket or they have worked with fins. A lot of people have also worked with cooling tubes, but mesh and expanding natural graphite compacts are not very, very much, have not been studied a lot. So fins and cooling tubes seem like the most popular arrangement that's out there. So this is just an overview of the existing systems. Okay, so this is MHHSR are just used as an acronym for metal hydride hydrogen storage reactor. Okay, this is just to cut down on writing a lot of stuff. So we have stuff with, we have tanks with external fins, then we can have something with like a single concentric cooling tubes. We can also have a reactor with foam. We can have longitudinal and transverse fins. We can have coil tube heat exchangers or multiple embedded cooling tubes as well. So when I was designing my system, I just thought let's start from scratch. Let's just see, what are the parameters that are out there. Okay. So what I did was I chose a basic system, a fundamental cylindrical tank here. Okay, and I fixed. So the thermal conductivity of alloy powders is very low because of the fact that they are powders. Okay, so you have like a lot of gaps in between. The effective thermal conductivity is as low as 1 watt per meter Kelvin. Okay, so I chose a basic system with K as thermal conductivity as 1 watt per meter Kelvin. I just assumed that it was undergoing post convection in air. and I chose H as 100 watt per meter square Kelvin. Then I chose supply pressure of 25 bar, and I chose external temperature as 298 Kelvin for absorption and 323 Kelvin for desorption. Okay. Porosity of the powders was chosen to be 0.5. Okay. So once I worked with these parameters, what I did was I gradually increased the thermal conductivity. So I kept all other values same, increased the thermal conductivity from 1 to 3, from 3 to 6, then 10, 12, and 15. Okay. Then I did the same with supply pressure. Work with 25, 30, 25, 40%. So the baseline is 1, for pressure it's 25, for temperature it's 298, and so on. Right. So what I did was, so similarly I worked with external temperature also, and in case of I also changed the heat transfer coefficient, reduced it also and increased it also. So as you can see that the percentage variation in hydrogen absorption is the maximum when we are changing thermal conductivity and when we are changing supply pressure. Right? So that means it is most sensitive to supply pressure and to changes in thermal conductivity. Now, supply pressure is an operating parameter and thermal conductivity is a design parameter. So, we also observe, if you see for thermal conductivity, when it is increasing by 2 units, from 1 to 3, there is a jump of around 10%. When it is increasing from 3 to 6, another 10%. Then 6 to 10, another 10% jump. But as we are increasing it further, the variation reduces. Okay? So here we realized that what we had to work with was thermal conductivity and supply pressure. One more thing, we did see that if you see here, if we go from natural convection to 500 watt per meter square Kelvin in case of H, there is a significant improvement. It's around like 20% roughly of change. If you go from this point to this point, because this point represents 4.023 represents natural convection. Natural convection in air. Whereas 500 represents some forced convection. I have not really specified what it is, just play it around with the parameters. Okay, so what we did was, like I said, we had a baseline system, performed simulation studies on this system, identifying the important parameters, then proposed a design improvement. Now, and that the sensitivity analysis, basically all the design and operating parameters led us to the final design. So here, we have some of the data that I've shown here. So as you can see that if we work with a baseline system, the reaction fraction, which is the percentage of reaction completion, is very low in case we are working with simply, with just natural convection and exit. Whereas if we are working with forced convection with enhanced K, means thermal conductivity is also enhanced and forced convection, then in that case we are achieving a much higher rate. So further studies led us to, I would just like to discuss this one interesting thing here. So if you see that even if we are using an enhanced thermal conductivity and we are also using forced convection, but we are still only at 54% reaction completion rate, whereas we would like to at least have 90-95% or at least 80 somewhere. So what we did was we also studied the effect of bed radius, okay, on the system. So when we study the effect of bed radius, as you can see that the temperature drop, this is temperature against bed radius. So do we have a pointer? and cost effective. There was not much maintenance involved. Like if you're going for those embedded cooling tubes, you need to get those tubes cleaned very frequently. Because if those tiny tubes, they get blocked, you can have possibility of leakage, and then, the alloy can get spoiled. There can be multiple problems. But in this case, the alloy was inside the smaller tubes, fans and RDK was absolutely no problem. We were very happy. But it did not last long. The reason was that we had used aluminum mesh inside the tubes during simulation. But इसलिए बोलते ना experience बड़े लोग बोलते हैं experience बहुत जरूरी होती है. When we think, I know everything, so it's fine. I thought that it was all good. But then we came to know from a very senior colleague that the problem with aluminum foams, or many foams for that matter, is that when you are trying to fill alloy into the tube, it gets stuck at places. It doesn't go through. And that seems reasonable also. I mean, we are talking aluminum foam systems which were smaller. So you have to fill in 1 gram of alloy, not a problem. But if you have to fill in 200 kg of alloy, huge problem. Right? You can't fill it uniformly throughout. It will take like weeks to just fill the alloy. So we had to drop this idea. We verified it on slightly larger systems, didn't work for us. There was huge, discrepancy in the alloy distribution. Like you can imagine now, अगर किसी गाड़ी के थ्रू आपको पाउडर डालना है, if you have कहीं कहीं ज़्यादा जाएगा, कहीं कहीं कम जाएगा, this will create a hassle. So we had to drop this idea. So we had to come up with something which could be as effective in transporting the heat, but not have this problem of alloy distribution. Already all of the characteristics were so beautiful. Like these are the streamlines for both the reactors. You can see that how the these are the cooling tubes. Previous one is this one over here where we had put in cooling tubes, right? So this is the characteristic for that. So you can see how it is how these cooling tubes are taking up all the heat. The streamlines are converting towards there, and in this case the streamlines are diverting towards the shed, right? So yeah. So what did we do next? So we figured that many foams are suitable for large-scale systems, but not in systems where alloy distribution can be an issue. So what did we do? We came up with an hexagonal honeycomb-based heat transfer enhancement which would be fitted into the reactor. So we calculated our output requirement, the volume of hydrogen required, subsequently the volume of metal hydride required. We had our uniform numerical simulation, we defined our problem and performed the data performance analysis, and then we implemented with our experimental studies. So this is the heat transfer enhancement that we designed. Okay, so this was this has a cellular structure like foams have, so it can be an effective heat conduction pathway. Then hexagons have a high specific surface area, means more area to volume ratio, so that means they are good for conducting heat without adding a lot of weight to the system, because this is also a problem. We can't add a lot of weight to unnecessary parasitic weight to the system. Already alloy 200 kg का है, उसमें अगर हम 330 kg का हम किसी का weight add कर लेंगे, that would be problematic for us. So we didn't want to do that. So we had to choose something which had a high area to volume ratio and also something which had high strength. The reason being that you are experiencing while the hydrogen is being absorbed into the system, it is expanding. When it is being resorbed into the system, it is being, it's experiencing stresses in a different direction. So basically you have side stresses on the system and it has to have a reasonably good strength. So this was the reactor assembly when we finally, came up with it. The design and HDE fitted into it at multiple locations. Okay. So these were fitted into it at multiple locations, and this was the top view of the side view of the reactor with the HDE. So this is we also have to use a filter for the hydrogen, right? Because when you're dehydrating the system, you do not want all the alloy to come out. Vacuum pump लगाएंगे आप एक साइड से तो all the alloy will also come out. So we need to have a filter in place which will stop the alloy from coming out. And this is the inlet. And these are the locations of the thermocouples. So these are the summary equations that we used since it is a fluid mechanics phenomenon. We do have the momentum equation in the form of Darcy's equation. We have the continuity equation. Then we have the absorption, resorption, and then the energy equation. Okay. So we also optimized the location of the heat transfer enhancements, but we did not, we just did a parametric optimization. Parametric optimization in the sense that we fixed the locations at different points and since we saw where the result was the best. So you can see that we placed the first we ran a study with the enhancements at 4 centimeters apart, 3 centimeters, 2 centimeters, and then finally 1 centimeter apart. But if we kept it, obviously the best results are when we have 1 centimeter apart because the reaction fraction or the percentage of reaction completion is very fast. But then this would mean doing many heat transfer enhancements and we couldn't afford that much in terms of system weight. We wanted the system weight to be lesser. So we went ahead with the 3 centimeter apart heat transfer enhancements. And if we saw the comparative performance, what we had was that in case of the this average reaction, so if we saw this at 400 seconds, here you can see that the maximum reaction fraction completion is 0.52, here it is 0.49. But also the area over which this maximum reaction fraction is spread is greater in this case as compared to in this case. So we found that this was a much better option than leaving the reactor blank with baseline scenario. So again we can see the improvement in the average rate of absorption. So here it is with the having heat transfer enhancement, it is much higher than without it. We also went on to study the effect of supply pressure on hydrogen absorption. So we changed the supply pressure from 25 bar to 40 bar, and we observed that it was increasing with increase in increase in pressure. Also, you can see that the average bed temperature increases first and then drops. So the reaction rate is highest in the first few seconds, releasing tremendous amount of energy, and then the reaction rate drops because, like I said, temperature increases, equilibrium pressure will increase, the reaction rate will drop, and also the fact that the many-hydride formation starts. So the overall reaction rate will drop, subsequently the rate of heat release will also drop, and the heat transfer mechanism, whatever we are using, that starts to kick in more effectively and take up the heat from the system. So you can see the average bed temperature increasing first and then dropping. So as PS minus P equilibrium supply pressure minus equilibrium pressure is the driving force. So we can see with increase in supply pressure, it is increasing. So then we also studied the effect of heat transfer coefficient under four different conditions. One was free convection in air, forced convection in air, free convection in water, and forced convection in water. So we found out that when we went from free convection in air to forced convection in air, not much change. But when we went from forced convection in air to free convection in water, massive jump, right? Over 100% 1% increase. Further, no change. This is looking, reason behind this is initially what happens is that the not like you need to have if you increase the heat transfer coefficient beyond this point, this is already extracting all the heat that is being transported to the periphery. Beyond this, the thermal conductivity or the transport of heat inside the system is not efficient enough to extract all the heat. So there's nothing at the periphery to be taken away. So that is why there is no major change here. But here we can see a significant or a radical rather increase. Then we also studied the effect of heat transfer fluid temperature. What we did was we changed the temperature of water that was being used to cool the system. So we had we tested at temperatures of 298, 278 and 288 Kelvin. Not much difference. It was something that we had seen in the sensitivity analysis also. Because in the sensitivity analysis we had seen that thermal conductivity was the most important parameter. Then just to see how our system was performing in comparison with other systems, we did a comparative analysis. So these are some of the systems that have been studied. So because when you are designing a system for wetting storage, you also have to see how much parasitic weight are adding. Like आप 1 kg hydrogen store कर रहे हैं in suppose 200 kg of a system. The system have other auxiliary weights also. Like in our case, we have the weight of the fins. Somebody else may have used different types of fins. So in their case, it might be different. In our case, for example, this heat transfer enhancement, somebody might have used cooling tubes. Then they also have to add the weight of the cooling tubes and the weight of water. So basically, you have to see holistically how your system is performing. So for example, we compare it to these guys. Say for example, Lopowski. I remember he had built a rectangular case in which he had put multiple, anti-hydraulic tubes. So his system and our system was relatively comparable because he has stored 642 grams of hydrogen and we have stored 667 grams of hydrogen. But in our case, if you see that the specific weight per gram of hydrogen, the system weight per gram of hydrogen is much lower in our case as compared to in his case. So that means that it was overall a better design. No, everything is evolving and we can obviously strive for a better and even better design. But this was something that we had somehow succeeded in. And you can also see I have even in terms of volumetric capacity, because volume की requirement है ना इस चीज को store करने के लिए. So how much volume is required is also an indicator of how well the system is catering to the needs of practical applications. So in our case again, in terms of the specific volume also, it was doing slightly better, but yeah, not bad. So this was again an experimental setup and how the pathways for allowing. So what we had basically was we had to supply hydrogen through this path. So valve 4 and valve 6 were open, rest of the valves were closed. So it would go from here and then pass through the mass flow meter and then go to the reactor during absorption. During the absorption, we had to close all these valves. V3 was also closed and V6 was also closed. And it would come from V5 and this pathway and then go to the exit. Okay. So because this was a unidirectional mass flow meter, so we had to take care of it. These are some of the pictorial depiction of the so this is what it essentially looks like. So we had also built this tank for for the protection of water part. Otherwise it was just lying openly. This is what it looked like, and after this we poured in the alloy into the setup. So we performed the same experiments. The studies that we have done numerically, we performed the same experimentally as well. So the results were matching. I will not really, bore you with them because we already, the same thing happened basically. But I will talk about something else which was very interesting. Yeah, so whenever we are doing, like you thought this was essentially a 2D study. How do we know that our study was, we did not have to consider the 3D component? It is an established fact that we can go for two-dimensional studies only. But what we did was, we did we placed the thermocouples radially and actually at different locations so that we could gather the delta T by delta R and delta T by delta X. Okay, so what we observed was that radial variation in temperature was 16 times the actual variation. So that means we could safely, ignore the whatever was happening actually and go for a two-dimensional simulation. Now, this was one of my good ideas of mine, and I like to brag about it. So, what happens when we don't have we do not have access to water? What do we do in that case? So, we thought of testing the system for evaporative cooling. Okay, those of you who are not from Kashmir would know that, like in North, I don't know now do they do it, but back when I was studying in UP, they used to do it. They used to have those straw mats, chick बोलते हैं, chick बोलते हैं उसको. So what they do is, वो पानी डालते हैं उस पे समर में, ठीक है? And then when the air comes into the room, it's colder. Yeah, so it is some kind of a humidification and also a cooling mechanism because the air has lost some of the heat, okay, to the water which is present in the chick, which actually evaporates. Okay, so it is you achieve this by evaporative cooling. So I thought why not apply the same principle to the reactor. So what we did was we covered our reactor in moist cotton wool. Okay, and we saw that the heat removal from the system, what will happen, the heat from the system would lead to evaporation of water in the moist cotton wool, which in turn would lead to removal of heat from the system. Okay, so when we did this with post convection in air, the results were very good. So that means if you are using a system for vehicular applications, you can cover it in a similar, blanket of water, and then post convection water, like vehicle के case में क्या होता है? It will always keep moving, and you will always have automatic post convection, right? So that means this could be an effective method of cooling where we have such a scenario. So these are the results that we had from here. So you can see that evaporative cooling with post convection here in red is almost as good as water with free convection. So, like in case of, so I've just plotted here the time that is taken to complete 80% of the reaction, 60% of the reaction, 40 and 20, so on. So here you can see if we leave the reactor in air under free convection, then we probably have to die before the reaction completes because it's taking forever. But if we go for like post convection, where is that post convection again? Sorry, this is water-free convection here. And if we go for evaporative cooling with post convection, so this is like quite reasonable. You can compare the two, and you can see how much difference it has from the base case scenario. So this turned out to be an effective method, and we are still working on it and seeing what we can do about it and explore more of it. Now coming to the desorption part. Just as the absorption reaction is exothermic, the desorption reaction is endothermic. So that means you have to keep supplying heat for effective desorption, right? But it also depends what is the rate of desorption that you want. I mean, it depends upon that also. So, but generally, yeah, desorption is an endothermic reaction. In fact, what we observed was that at the surface of our reactor, the temperature was as low as -11. Okay, it was like very cold. So we used resistive heating as a heat source, and we used heated water as a heat source in this case. And we found that the heated water was showed, Like if we use that water at say 323 Kelvin, which is 50 degrees Celsius, the improvement in the reaction rate was much better than as compared to if we used resistive heater at 50 or 60 degrees. But my theory is I still feel that the resistive heater would have worked better. What we did not take into account was the contact resistance. I mean, we either have to get a resistive heater custom made for such things. Because what will happen if you use a normal band heater, there'll be too much contact resistance. बहुत ज़्यादा air जमा हो जाता है caps में, and that prevents effective heat transfer. Next thing was also there was sagging on the other side, the underside bit, because when you roll it, wrap it around the reactor, on the downside the gravity acts and it will sag, so the contact is not maintained as effectively. So these are some things that we should have taken care of. Also the fact that there were gaps due to finite flexibility, because the band heater has a finite flexibility. You have to find a better way of covering the whole surface in some way. Although again, like I said, the results show different, but I still feel that there was scope of what we could have done differently. Now all of this exercise has been done to power a fuel cell. So we also have to see whether our system is actually capable of powering a fuel cell or not. So So, it's been happening like okay. So for our fuel cell, which we had in mind for this entire study, the wattage per cell was 41.1 watt. So for a 2 kilowatt fuel cell, if we were to run it for 5 hours, because this was a 20 kilowatt hour system. So the cells required were 49, and the hydrogen required was zero point 0.5 standard liter per minute per cell. So total hydrogen required was 24.5, and this came down to 5.2 into 10 to the power minus 5 kg per second. And we saw that this was the mass of hydrogen dissolved, and this is the line where we have the where our fuel cell, this is the fuel cell requirement, the dotted line. So we can see that in the initial phase, our hydrogen desorption rate is much higher than the fuel cell requirement actually, and we can use a buffer tank to store it. And as the reaction drops, we can turn on our heat source further, so that as you can see that for 323 Kelvin, the resorption rate is maintained at much higher than the fuel cell requirement, up to 4,000 seconds. So if we increase the temperature beyond this further, we will be able to maintain the fuel cell requirement. Also, not to mention that the hydrogen that we will have stored in the buffer capacity can also be used. So, thank you all for having me on Rozo Mein Sunna. Thank you so much. So are there any questions? It's not actually. I'll just go back to that. Yeah. Can we make a blended kind of a structure so that we can enhance? Of course, we can blend it in that. I mean, in what sense? In design. Because as is now has been structure has shown a very good kind of a comparator when compared with the other design. Yes, sir. If we just blend to but then, like for example, you can use fins and cooling jackets. Suppose in our system only, if we add external fins, the performance would definitely improve. But you also have to think about how much weight you're adding, because I don't know, personally, I don't like to work with fins because they always come with a efficiency. We that is in the pipeline because that is something that we need to do. Yeah, yes, yes, definitely. That is in the pipeline. Answer also costs. I mean, because that is one inhibiting factor. The alloys are very expensive, so that is one inhibiting factor. But yeah, we can add that, like you add multiple. Yes, sir. So the one that we worked with was lanthanum cerium nickel. Lanthanum cerium nickel alloy. We got it from China. It's expensive, definitely. Sir, it was for, I think we got 50 kg for $200 or something. 200. Around yeah, 16,000 for, so how much would that be for 1 kg? Can you divide it by 50? But yes, no, these are not nanoparticles. So 16,000, like the reactor that we made was for 80,000, and if you add 16,000, so it is around for 20 kilowatt hour system, you would be it would be around a one lakh, right? G G G. So we would have to do that, but then like this technology is still in a nascent stage, so right. So yeah, you can add multiple, and the 667 is this is like, different for different systems. Basically, this is we had designed it for 667 grams. They had designed it for 642. This is not what is important. The important parameter is this. So, for example, this guy, his system weight per gram of H2 hydrogen is around 500, right? Close to well, over 500. For us, per gram of hydrogen, it is what? Yeah, 200 grams. So that is what is important. So this is in grams, not in kgs. Yeah. Reverse की time पे वो हटाना पड़ेगा. Or you can alternatively have this kind of a mechanism. Suppose you go for a resistor heater, okay, which you can already keep in place only. हाँ, बस फिर वो मतलब you have to turn it off when you are using this thing. Yeah, anything else? Aluminium is lightweight. Everything else was very heavy. Besides, I don't know if you see like these honeycombs, they're used essentially in for structural strength in aircraft wings. Okay, the reason behind this is for lightweight only. So that is what. So, like when I said parametric optimization, you know how optimization is done. But in this case, because there are too many variables involved, we could not go for the optimization route that is normally taken. So we had to do a parametric optimization in the sense that we tested it for different parameters, say at 2 centimeters, 3 centimeters, and then we saw which result was the best. So, no, not a function-based optimization. Expanded natural graphite, it is graphite, is a good conductor of heat, right, and electricity as well. So in case of expanded natural graphite, these are graphite sheets which are mixed with the alloys to improve the thermal conductivity. So when you have a mixture, the effective thermal conductivity will be the sum of the two conductivities based on how much ratio, volume ratio they are in. So that's why effective this expanded natural graphite is added to improve the overall thermal conductivity. Thank you so much.
Thank you very much, ma'am, for such an informative session. Now, I would like to welcome Dr. Mahesh Sardar to be felicitated by HOD sir.
Actually, as Gautam told you in the beginning, Dr. Mahesh was our faculty here in 2014, and Ms. Bisma was also our faculty. So they were just colleagues. So I met both of them. Aye. So Bisma will just take a photograph. Aye. Please a photograph. Tell Bisma. So they were, their office was the one that was so excited. Thank you, Anand. Thank you. Okay, so now we have a visit to chemical department. In chemical engineering department, you have to just see over after that it's because we'll show you something. So we'll be expecting visit. So what about that article discussion? Huh? What's the article discussion? Oh, you have MCQ also. ना वो तो बताया क्या है? MCQ भी है. वो lab visit का report भी है. वो कब finish है? Because that's very important. हाँ? क्या बजे? In the morning we have two sessions. Both अच्छे हैं ना. I don't want that you should miss those sessions. One session is on measurements, flow measurements in micro product channels. Second is laser-based techniques in external fluid mechanics. So in the morning, we have had those things. Afternoon, man.